Hello everyone, thanks for watching this video. This is the video recording of the tutorial which is titled Unbiased Learning to Rank on Recent Advances in Practical Application. This is a tutorial we presented last year at SIGIR and then at FIRE, and this is the recording for the tutorial at Wisdom Conference. Alright, so who are the presenters? So I'm Shashank. I'm a PhD student at the University of Amsterdam. The co-presenters are Philipp Hager. He's also a PhD student with me, the University of Amsterdam. Then we have Jin.
Hi, everyone.
And Jin, she was a PhD student. She recently completed her PhD. Now she's doing a postdoc. Then we have Ali. He's a research scientist at Spotify. He was a PhD student before. And finally, we have Harrie.
Hi, everyone.
Okay, this is the, if you want to scan, this is the website for the tutorial. It's also mentioned in our website, Wisdom Tutorials website. Okay, so let's start with the objective of this tutorial. So the main goal of the tutorial is first to introduce the fundamentals of unbiased learning to rank. And more importantly, we want to discuss the recent advancements in the foundations and some applications of unbiased learning to rank. Now, this is a high-level goal. Some specific goals are, we want to introduce the latest forms of biases that were published in recent last 3-4 years. And then we want to introduce the latest estimation techniques which are used to correct for the biases. Then we'll discuss some real-world applications of unbiased learning to rank and its connection with fairness in ranking. Finally, we'll discuss the future and some potential areas of improvement in unbiased learning to rank. Okay, that's the tutorial. That's the overview. Now, these are the sections we'll cover. We'll start with the introduction to unbiased learning to rank. We'll talk about fundamentals. Then we'll talk about some of the latest biases in user interactions. And then we'll talk about some estimation methods which are used to correct for the biases. Then we'll talk about some survey applications of unbiased learning to rank. And then we'll discuss its connection with fair learning to rank. And finally, we'll conclude with some future directions.
Thank you, Shashank. I'll continue now with the introduction section of this tutorial, where I'm going to explain the basics of counterfactual learning to rank before the rest of the tutorial will go into the recent advancement. And I'm going to start by showing you or visualizing the what the basic ranking system pipeline looks like. So what we have here is all the way on the left, we have the items that we're ranking. This is a web search example. They're going to be documents. Those documents are represented by features. So there's a feature or embedding lookup representation phase. And then those features are being used as input for a scoring function that will give a score to each of the documents. Based on those scores, we sort the documents, so the highest scoring document goes first, and this gives us our ranking, so our ranking of documents. Of course, this then turns into the results of the results page, right? So the top K of these items will be displayed to the user in this results page layout. So this represents sort of the stages, or gives a model of the stages through which a ranking pipeline goes. Very often this is the last stage of ranking, so there might be more stages before that, for instance, how to select the documents. We're not going to go into that here, but the structure that you see here occurs in almost any place where there is search or recommendation. So if you're looking for a product online on an e-commerce website, we're not ranking documents, they're now products, but it's the same steps there. Similarly, the results page may not be these 10 blue links, maybe it's a grid layout, but again, there's a sorting here and ordering the same way. You can also go to other media, right? So if you're do ranking videos or images, it's the same idea. So the videos will be displayed by features. We have a scoring function, gives a score. We sort to get a ranking, and we display them in a recommendation page in this case. All right, so ranking systems are really at the basis of search and most recommendation systems. Nowadays, they're crucial in navigating the internet. They can really help us to retrieve information or find our way of course, this enormous web that we have. The performance of these systems is therefore very important. So if they don't rank properly, it can really affect user satisfaction or engagement. It may find it very hard for people to find what they're looking for or to find something interesting. So it's important that they perform well. Typically, the goal of a ranking system is to put the most relevant items on the top of the ranking, so to sort according to relevance. Nowadays, we also see very often it being balanced with other objectives. You can think of diversity, novelty, or fairness. We'll talk more about fairness at the end of the tutorial, but for now we're going to focus on ranking according to relevance. Right, that's a ranking system. As I said, it's important they perform very well. Therefore, there's a need to optimize these models. And we call that optimization learning to rank. Now, here is the standard learning to rank pipeline. And you can see it's very similar, but now here at the end, we have the ranking being compared with labels. So this would be labels that come from expert judges that tell us how relevant a document is. And then based on how relevant it is, we could compute a metric. For optimization, we would put it into a loss. So we have a learning to rank loss. Usually these are categorized as pointwise, pairwise, or listwise. What's important is that loss can give us a gradient so that we can do gradient descent. So we can look at what the loss tells us how the system should improve, and that way we can improve both the scoring function or the way that feature extraction is being done or the embeddings, etc. This is standard learning to rank. What we're going to talk about in this tutorial is actually a slightly different setting. Instead of using relevance labels, we're going to be using user interactions. So we're going to do learning to rank from user interactions. So learning to rank is really a subset of machine learning where we optimize ranking models. The traditional way, as I just shown you, is with annotations. So we call these annotated data sets where we have expert relevant judgments that tell us how relevant a document is for a query. So we call that a judgment for a query document pair. The advantage of this approach, and the main reasons why it remains relevant today and for the future probably as well, is it's very reliable. You have a very reliable ground truth because you usually just trust your judgments. You have control and consistency, and you have very little noise compared to interactions. These labels are very stable in that respect. However, this is also a very limited approach. So creating annotated data sets is very expensive. They are stationary, right? They're static. So if there are changes in relevancy, you have to update your data set, which again then is expensive to do. There are many situations where it's unethical due to privacy reasons to create a data set this way. Think about searching through personal documents like emails or someone's personal photos, something like that, where you can't have like a third-party expert judge look at whether something is relevant or not. These are also settings where it might be unknown what's relevant for an expert, right? Because it's very personal. If you're doing any personalization, we don't really have an objective way to measure what's relevant. And in web search settings, very often users actually disagree with the labels. So the disagreement may not be very big, but there is some disagreement, which tells us that if we were to perfectly optimize according to these labels, we would still have a mismatch with the actual user preferences. So that means that supervised learning to rank is not available to all practitioners or not applicable to all situations. So there is a need for an alternative approach, and that's where learning to rank from user interactions comes into play. Specifically, we're going to talk about counterfactual learning to rank. So that's where my introduction to this topic starts. This is one of the main ways to learn from user interactions. Specifically, counterfactual learning to rank is a setting where we want to avoid deploying a model. So we want to estimate how well a ranking system is doing based on interaction data gathered by a different ranking system. So the system we're evaluating does not have to be deployed. We're using the data from a different system to evaluate it. And if we can evaluate it, we can estimate. That basically means we can estimate its performance. That usually means we can also maximize that estimated performance. So evaluation, optimization sort of come together in that way. But there are some serious difficulties when you're using user interactions, and these are noise and bias. Interactions are full with noise and bias. Noise is generally not that big of a problem. This is the kind of error that goes away if you have more and more data. So you can average away noise pretty much, but you can't do that for bias. So if your data is biased, you really need statistically unbiased estimation. When I say bias here, I mean statistical bias, by the way. There are also other forms of bias. I'm limiting myself to statistical bias. The most important bias, and the bias that will the field started around basically, so the most common in early work, is position bias. What we mean with position bias is that when you show users a ranking and you let them click on while they're searching, the position at which you show an item has a really large effect on the interactions you see. And one of the main reasons that happens is because users usually only look at the top results. So here is a eye tracking study, and it shows us that most users, almost all of them, look at the top 2 results. But if we go down to the bottom, we see that very few people actually look at the result number 8 or 7. So that means if they're not looking, they're also not going to click. So we're going to see less clicks there, but it has nothing to do with how relevant these items are. It's just that they are displayed at the bottom of the page where people often don't look. There are more reasons why position has an effect. We're going to talk more about that later. What's important is the reason that we call this bias, right, is this mismatch between the click-through rate and relevancy. We want to know relevancy, but we know that click-through rate, it doesn't exactly indicate relevancy. It often says more about how a document was displayed than how relevant it was. That's a problem, right? Because we just want to know that relevance part. The earliest work looked at position bias as a form of selection bias. And you can think of that as a selection filter. So this is what we call the rank-based examination click model. It's the equation you see here on screen. And it basically says we can decompose the probability of a click into the probability of examination, whether someone looks at a result, considers it, and the relevance probability, whether it's actually relevant for what they're looking for. What's important here is that what these probabilities are conditioned on are different, right? So the examination probabilities is conditioned on K, the position at which an item was shown, and the query Q. So not the item itself, not the document itself, which makes sense because you can't decide to look at an item based on its content because you don't know the content before you looked at it. That would be the idea. And the probability of relevance. So which is conditioned on the document and the query. So relevance, it doesn't matter where an item is being displayed, how relevant it is, right? So it should only depend on the document and the query. So this way we can decompose it into the relevance part that we care about and the examination part that's sort of biasing our click probability. What's important here is that this equation is invertible. If I want the relevance probability, I can take the click probability and divide by the examination probability. We're going to use this property later. I mentioned that you could see this as a filter, right? So the idea is that this examination probability drops if we go further down the ranking. So here on the right, it would be an example of that. These numbers, of course, are made up, right? But just for the example, right? We have most people looking at the top. So let's say 100% of people look at the top 2 results. And the further down the list we go, the fewer people are looking. So over here we have 50% and then 40% of people left. Thinking of this as a filter, you would say, well, if people click when they see something that's relevant, you're going to see if 50% of the people clicking down here, just because 50% of people made it that far down the list. So you would expect to see half the number of clicks that you would see up here on the top of the ranking. That's how we see sort of position bias as a filter. All right, let's look at the simple sort of setup so that I can first show you the wrong way to do it and then the basic way to deal with this position bias. But first, the goal for this setup is I want to estimate the discounted cumulative gain of a ranking Y. So I have my ranking Y here, and I'm going to use the notation Y and then square brackets K to indicate the item at position K in ranking Y. The discounted cumulative gain, this is slightly different because I'm not using the annotation labels, but you can think of it, I'm using U, you can think of it as a utility, something that we want to maximize. We have, we're going to sum over every rank in our ranking. And then we have the probability of the item at that position being relevant divided by log 2 the rank plus 1. This is standard discounted cumulative gain discounting. And this would give us the DCG of the ranking, which is a very common metric used in ranking. This is what I would like to know. Of course, I don't know the probability of relevance. If I knew the probability of relevance beforehand, I wouldn't have to create a ranking system. I would just rank according to that, right? So we can assume we don't know the probability of relevance. The data that we have available, so the data that I can use, is interaction data from a previous production system. Specifically, I'm going to assume to have queries that users issued, rankings that were displayed to the users in response to those queries, and a clicking signal indicating where did users click when they were shown this ranking for this query. So that's the data that we can use. This was gathered using a different system than the one I'm gathering up there. So Y bar, with the bar above it, that's the one that we displayed. Y without the bar is the one that I want to evaluate. So I'll start with the most straightforward, but also the most naive way to do this. That would be to ignore everything I mentioned about position bias and just say, well, click frequency is going to indicate relevance. It's going to be proportional to relevance. So I'm going to take my average click-through rate of a document. So I just take the average click signal, right? And that's going to be my relevance estimate. I can plug that into my utility function, right? I just replaced the probability of relevance with this average click-through rate. And now I have an estimate of the relevance of this document, or an estimate of DCG to be specific. This is, well, this gives you a biased estimate. That's why we don't want to do this. And what I mean by biased estimate is statistically biased. So that means the expected value is incorrect. So incorrect meaning not the thing I want it to be, right? So if I take the expectation over clicks, you remember a click was in this model examination times relevance. This is a very simple model. We'll have more complicated models later. But in this model, it's examination times relevance. If we take the expectation there of this thing over here, right, it's just going to be the expected click probability. We can simplify that to the so the relevance part, it doesn't depend on what the logging system did, so that we can take it out of the expectation. What's left here is what were the rankings that the logging policy showed, and what was the examination probability under those rankings. So what's the expected examination probability under the logging policy, multiplied by relevance. Now, if you remember, what I wanted to have was only the probability of relevance, but now it's being weighted by this term in front of it. And that's the filter, if you remember, right? So we have a probability here, so a value between 0 and 1, that's multiplied by our relevance. And this value depends on how the logging policy displayed items. So this is a problem. We want to get rid of this factor when we're examining. And the most common way to do that is through inverse propensity scoring. Or I should say the basis of the field, we have inverse propensity scoring. Inverse propensity scoring is very broad. You might have seen it in literature on causality. It's very common in, for instance, medical literature in this topic. And you can apply it to data with selection bias. That's data that's incomplete. You don't observe everything. And there's a systematic pattern in what is being observed. So it's not just randomly you observe things. There's a pattern in what you observe, what you don't observe. The solution through inverse propensity scoring is to weight observations inversely to their observation probability. And what weighting is going to do is you can pretend you saw something more often or less often than you saw it, right? So if I see a click and I give it a weight of 10, I'm pretending I saw that click 10 times. If you do this inversely to the selection probability, they're going to cancel each other out. So in expectation, the selection is not going to have an effect, meaning the expected value doesn't include, is not affected by the logging policy anymore. It's what we want. basically we're doing the same thing selection probability does, but then in reverse through weighting. It's the same underlying idea as for importance sampling. So if you can think, if you're familiar with importance sampling, this is the same basic idea. What does it look like for learning to rank? Well, here we see how this was being applied in the first counterfactual learning to rank works. So each click is going to be inversely weighed by the examination probability based on how it was displayed. So my IPS estimate of relevance is again an average over clicks, but now each click is being weighted by the examination probability of the conditions under which it was being displayed. So if this item was displayed in a place where 50% of people were looking, we have 1 divided by 0.5, we weigh it twice. We pretend like we saw 2 clicks instead of 1. And then I can plug this into my DCG estimate, and I have an estimate of my performance again. All right, so this is unbiased. And before I show you that it's unbiased, let me make sure that you understand what I'm saying. So we're dividing here by the probability of examination in the displayed ranking. And it's important to keep those separate, the displayed ranking and the ranking we're evaluating. So the weight depends on the displayed ranking, so the ranking in which the item was being shown to the user when we were doing logging. So that's specific to the way we did logging. Y without the bar is the ranking that we're evaluating right now. So that's a new ranking. These are different rankings, right? So one of them is specific to the logging. The other one is just what we are trying to evaluate. It could be any ranking. Okay, so bear in mind they're different. Now let me show you how it's unbiased. So if we take the expected value again, you remember, right, this click variable, we get the probability of a click there, which is examination times relevance. So I can replace that, we replace that here. But because we're already dividing by the probability of examination, in the expectation, these two terms now cancel each other out. So I'm just left with the relevance. So the basic idea is that by weighting these clicks, the reverse way in which my expected value is affected, I got rid of the effect in expectation. Another way to think about this is I'm doing the opposite of what the filter is doing, right? So when the filter is only giving us 50% of the clicks due to examination, I'm going to take the clicks I see and I'm multiplying them by 2. So I expect to see 50% of my clicks, but now I multiply it by 2, so I expect the number to be representative of 100% again. If it's 40%, then I do 2.5 and so forth, right? Vice versa, if it's 100%, right, if everyone is looking at it, we multiply by 1, we don't do anything because we think we already have all of the clicks. This is the basic idea behind inverse propensity scoring for rank. I want to be clear before I continue. I mentioned being unbiased. I've talked about the expected value. I want to be very clear. When I say an estimator is unbiased, I mean statistically unbiased, and it means that does not mean it's without error. I don't mean that now if you get an estimate, that estimate is correct. Right? We still have errors here. It also does not mean that I expect the estimator to be correct, that like more than 50% of the time you're correct or something like this. No. It only means that the expected value is the correct value. So if you compute the expected value, it is going to be right. So there's a very famous visualization of this. You can see the citation below that represents this as targets, right? So if I'm trying to estimate the center of the target, but all my estimates are off-center and they're very close together, they're biased because they're off-center, right? My average estimate here is somewhere over here, and it's low variance because all of the estimates are going to be close to each other. So so this would visualize a biased and low variance setting. An unbiased setting with high variance would not put all of the points in the center, even though it's unbiased, right? It just means that the average of all the points is in the center. So if we take the average of these points, we end up here in the center. But it's high variance. So in this case, they're spread out. you will only have access to one of these estimates, right? So we have our one data set usually, we compute it, and we would end up in one of these spots, but we don't know which one. So we can't assume that we're always ending up in the center, but what we can say is that sort of in expectation, if we take the weighted average of where we expect to end up, that is at the center. What you would prefer is an unbiased low variance estimate, right? So this is an estimate that the center is right and everything is very close to it. What I want to point out is something that's usually not included in these examples is there's another setting where you're unbiased and you have high variance, but none of the points are actually near the center, right? It could be that you're in a situation like this where wherever you end up, you're going to be very incorrect, but still on average, if you took the weighted average of where you could end up, you would still be all right. Okay, so luckily, usually unbiasedness in our setting also means consistent, which means if you have more data, you're going to converge at the right place. But when I say something is unbiased, I just mean the expected value is correct. That's all. It doesn't mean that when you perform the computation, you're going to be correct. It doesn't mean sort of that most of the time you're going to be correct. It just means that if you were to repeat this experiment many times, get a new data set, recompute it, and then take the average, we would expect sort of your value or expected value to be right. Okay, I already mentioned variance, right? So the thing is, variance is also something very important we shouldn't forget about because there's very often a trade-off between bias and variance. Very often, becoming more unbiased means increasing your variance, and both of them bring in error, right? So you probably usually want to balance those two. It can be beneficial to have a little bit more bias if it means that your variance greatly decreases. To give you an example on this slide, right, it's maybe better to be in this situation here on the left than in the situation on the right. Because even though we're off center here, we're closer to the center always than the points over here. So it might be better to be a little bit biased, but to greatly reduce variance. And because of this reason, very often we want to deal with low propensities. Low propensities mean very large inverse propensities. So if you think of this examination probability, if you have a 1 in 1,000 examination probability and you see a click, you now have to multiply that click with 1,000. And this basically means that you're blowing up the noise in that observation. If you were to take 1,000 clicks and take the average, you're reducing noise, but now we are doing the opposite. So we're increasing the noise. This results in very high variance. A very common solution to this is, and a very simple one, is to clip the propensities. So instead of dividing by the probability of examination, we would divide by the maximum of the probability of examination and the parameter tau. And this can make sure that we don't get these enormous inverse weights. You can say, I don't want to give a weight more than 100. And you set tau to 1 divided by 100. And that can really prevent variance. But it will add some bias there. But it's very often a good trade-off depending on how much data you have. Okay. All right. Finally, let me show you, give you a visualization of sort of what happens between these methods when we put them in a very simple toy example, right? So what I have here is a simulation on a basic data set where we're optimizing the average relevant position. The lower, the better. So this is the average position of a document that's relevant. On the x-axis is the number of training clicks in my data set. So I'm simulating a very small data set. Let's say I only have 1,000 clicks or all the way up to 100 million clicks. And please note this is also on a log scale, right? So each step here is a times 10 size of the data. This is not an online experiment. It's just I'm simulating different data set sizes to show you the effect of how much data you have. Down here we have the oracle line. This is the best performance you can get on this data set. I know it because it's a simulation. In a real world setting, you wouldn't know it, obviously, right? This red line up here is the production ranker. This is what I use to simulate clicks. So clicks have been gathered using the ranker up here. You can see there's quite a big performance gap, so we can still improve this production ranker quite a bit. Then this blue stripe line is the naive approach, ignoring position bias altogether. And surprisingly, maybe you can see it improves the production ranker actually, but it gets stuck very quickly. So here we go from 10,000 clicks up to 100 million clicks, and we see no improvement. This is very typical of optimizing a biased loss. It basically means that it's optimizing something different than what we want. It's not optimizing ranking performance, it's optimizing something biased. As a result, it gets stuck, or adding more data doesn't help. This is very typical. So if increasing your data by a very large factor doesn't improve your performance, it could very well be because you're stuck in a biased minimum, or the minimum of a bias loss. Then we have inverse propensity scoring, which is unbiased in this setting and consistent. We can see that because here at the end, it's this cyan line, it has perfect performance. But if I go to the lower data set side, or on the left, we have really bad performance. This is the bias variance trade-off. So there's a lot of variance here on the left, where my data is very small. But here on the right, when we get more data, the effective variance disappears, because variance is something that you can get rid of if you just have more data. So even though it's unbiased, it's doing much worse than the biased naive loss here. And this is clearly a variance problem. Finally, we have clipped IPS, which is this purple line over here. And what I've done here is the clipping factor tau is something that increases as we get more data. So that basically means the effective clipping becomes smaller and smaller the further we move to the right. As a result, it converges at the same place, right? It keeps the convergence of IPS, but here on the left, it behaves more like the biased naive loss. That's actually not a coincidence. They're very similar at this point because they're both low variance biased estimates. And as you can see, this gives us sort of a best of both worlds. So initially we have this better performance, but instead of converging on the wrong place, by sort of removing the effective clipping slowly, we can still converge to the right place without getting variance sort of overwhelming the optimization. So this is very typical. These are very typical performance curves of biased and unbiased losses in learning to rank setting. This was an overview of sort of the basics of the field before we go into the rest. I'm going to give you a summary, and then we're going to dive into the advancements. The first thing that I would like you to remember from this first part is that ranking is vital to search and recommendation. Ranking systems are incredibly important there. And there's also a need for learning to rank from user interactions. It's very important in many places where we can only learn from user clicks, or where it's the best way to learn, that we're able to do that. However, we have to remember that interaction data is always noisy and biased. Most data is, but especially interaction data. And interaction data in a ranking setting, you can expect it to suffer from heavy position bias. So if you're working with clicks on a ranking, you can expect that the position at which you showed items is going to have an effect on the click-through rates that you observe. I've shown you the most basic technique in counterfactual learning to rank, which is inverse propensity scoring for ranking that can unbiasedly estimate relevance from clicks. This is really the basis for the field. If you are familiar with this area, you probably already heard about this part. Now, the rest of the tutorial is going to sort of expand on these areas. We're going to look at more biases, more counterfactual estimation estimates and inverse propensity scoring, real-world applications, and also bring in fairness into the mix.
So in this next section, we're going to talk about biases in user interactions. Specifically, we'll cover first estimating position bias. So if you remember in the introduction, we introduced inverse propensity scoring, where we divide a click by the probability of examining that certain item. We need to estimate that examination probability, and we will cover 3 different kind of ways to estimate this probability. And then afterwards, we will go on and talk about biases in user data that go beyond this kind of simple position bias that we've covered so far.
All right, let's discuss estimating position bias. So, as we mentioned in the introduction, inverse propensity scoring requires an estimate of position bias in our data. Let's formalize this a little bit. So far in this lecture, we have assumed the position-based model. Under the position-based model, a click on an item depends on the position of that item and the relevance of that item. So here we cover this in red kind of. We have the probability of examining an item at a given rank, and then the probability of that item being relevant for the current query. This user model makes two assumptions. The first one is the examination hypothesis, where we assume that users click only on examined and relevant items. The second one is that in this model, observing an item only depends on its position and, for example, not on other items. This is a very strong assumption, and we'll later relax this in this section when we, for example, talk about cascade models. The first way we can estimate position bias under the PBM assumption is online randomization. So remember that item relevance is independent of other items in the PBM, and observing an item only depends on the item's position. Thus, if we display an item in two different positions and we observe a difference in click, this difference in click-through rate is only dependent on the position bias and not, for example, because a more relevant item was shown above the current position. There are multiple different ways to do online randomization, and they have all different levels of evasiveness, like how much they might impact our user experience. So the first method we can cover is randomizing the top k items. So here in this example, we have 5 different items, A till E. Every time we display these 5 items to the user, we just randomly shuffle them. What happens then is that in expectation, all items will be displayed at every rank an equal amount of time. So in expectations, all ranks in a way have the same relevance because all documents have been displayed there the same amount of time. If we now observe a difference in click-through rate over these ranks, this difference in click-through rate is actually proportional to our position bias and not due to, for example, the difference in relevance between those different items because all ranks have the same documents displayed. However, you might imagine that just uniformly random shuffling items every time we display them has a very negative impact on user experience. And in certain use cases, for example, your web search results, you might have very different expectations of your search engine. Therefore, it's more common to randomize, for example, just parts of your ranking. For example, pairs. There are algorithms to just swap neighboring pairs, or a very common way is to randomize each item with a certain pivot rank. So this is the pivot ranking method. Here in this example, for example, we have a pivot rank of 3, and every time we display the ranking, we select an item at random that we then swap with the item at position 3. So here we see the document C being ranked to all different positions. What we observe then over time is basically the click-through rate of an item in its original position and when it was swapped to the pivot rank position K. And the click-through rate difference between those two different positions, basically without the swap and with the swap, is then proportional to the position bias ratio between those ranks. It's not equal to the actual position bias, but we only need a proportional position bias for inverse propensity scoring to work. However, as you can imagine, we can lessen the impact on user experience through randomization, but in every case, there is still a slight probability that, for example, our most relevant result will be swapped to a lower position. So the main question is, can we avoid online interventions altogether? And the answer is that oftentimes, yes, because actually we perform implicit interventions in production systems all the time. For example, we might have had a number of previous production systems that probably did slightly different ranking decisions. We might have tested 2 different models in an A/B test, and they probably made different ranking decisions. Otherwise, we wouldn't have A/B tested them against each other. Or we might even have a stochastic production policy that samples a ranking every time we display them to the user. This is something we'll cover later in this tutorial. So in a lot of times, we have variability in our historic log data that we collected from our production policy. And we can use this variability in our log data to estimate position bias. The main method to estimate position bias from historical logs is called intervention harvesting. In intervention harvesting, we construct something called interventional sets, where we collect items that different rankers placed in different positions over time. Take this example here. We have 3 rankers that were tested in an A-B-C test. So they ran at the same time in our production system, and they showed the same items to users that were randomly assigned, for example, to ranker A or ranker C in the setting. You might see that ranker A and B made quite similar rankings actually over time, but ranker C chose to present items quite differently. What we can use now in our log data is, for example, we can see that item B was displayed in position 2 here by 2 rankers, but ranker C placed it in position 1. So by comparing the click-through rates between item B being in position 2 and being in position 1, we can say something about the position bias between the 2 ranks. And if we collect enough items that were swapped across our rankings, we can actually compute the full proportional position bias. A main problem in intervention harvesting is, as you can see, is that not all items appear an equal amount of time at different ranks. So we actually need to correct for this unequal exposure of items across positions. Another assumption that we make when we use intervention harvesting is that these different rankers that we are using here must not handle different queries or users. Meaning, if we, for example, always assume that a certain type of user has a certain preference for items and we always assign them to a certain ranker C, for example, and a completely different type of user to ranker A, we observe click-through rate differences that are actually not due to the variability in the positions, but they might actually be an expression of, for example, item relevance. So we need to make sure that these different rankers are comparable when it comes to the user group. There are multiple extensions to these methods. One extension, for example, handles user context. So you might imagine that in certain contexts, users might want to explore deeper down in a ranking. So you want to have a different position bias estimate for these settings. Or there are also methods to replace, for example, this reliance on having different A/B tests with a single stochastic policy for estimation. So far, we've been looking at bias estimation and relevance estimation as 2 separate tasks. First, we estimate bias, and in the second step, we use that bias, for example, to estimate relevance using inverse propensity scoring. However, there are also multiple methods that infer both at the same time. The first thing we'll cover is click models. It's like kind of an older established method, and the extension for that is regression EM. Later in this tutorial, we'll also cover 2 tower models, which are kind of a neural network instantiation of these older click models, and we'll also cover the dual learning algorithm in this section. Click models are a very traditional method when it comes to web search. They were proposed over 15 years ago, and their goal is kind of to, as the name implies, predict clicks on a list of items. Click models explicitly encode how we think users might interact with a given list of items. And we typically use the framework of probabilistic graphical models for that. Or in recent years, we might also implement them with neural networks. For example, here on the right is the graphical model for the position-based model, the PBM, that we've used so far in this tutorial. And we can define our variables that we might think impact our user behavior, and then we infer the parameters using things like expectation maximization or stochastic gradient descent. One problem with traditional click models was that they require a lot of observations of the exact same query document pair. You can imagine, for example, a given search query and a given list of items that were displayed, and we would count the impressions of each item for that particular query and the clicks for that particular item. So it's a very high-dimensional parameter space, and we need a lot of repetitions of the same query document pair to make this estimation very well. This is where regression EM came in. This is a method that, instead of having a single parameter for each query document pair, tries to generalize over multiple query document pairs by using item features. So here, for example, on the right, you can see the PBM, where we replaced the relevance parameters using a regression function where we take the query document features xd and the function f, and we try to predict the probability of these items to be relevant. The problem here is now that our model has a relevance model in there that we need to properly specify. And for example, if we underspecify this model, for example, as a logistic regression, but we actually would need something more expressive, then we might introduce bias into our estimation procedure. Another thing that we'll cover when we talk about two-tower models is that sometimes using a strong logging policy to collect the training data we use for regression EM might be also a problem in this setting. The last method we want to cover in this setting is called the dual learning algorithm. The dual learning algorithm also jointly infers bias and relevance, but not using click modeling, but by using IPS. If you remember the position-based model, a click is dependent on the probability of observing an item times the probability of the item being relevant. And in IPS, we weighted our click by our position bias. We can just invert basically this formula and use this also to estimate our position bias in the first place. So what the dual learning algorithm does is in the first step, we basically do classic IPS. We take our clicks and divide them by our bias estimate to get an estimate of item relevance. In the second step, we do IPS again, and now we reweight our clicks by our relevance estimate to get a better estimate of our bias. At the start, these estimates won't be very good, and typically the parameters are just initialized at random. But over time, we might obtain a better bias estimate that will lead to a better relevance estimate, and that might lead again to a better bias estimate. And so we iterate these two steps until the model converges, basically. This is quite similar in a way how also regression EM works, but on an implementation detail, this method uses a listwise optimization method, for example, for the relevance estimate, and it's optimized using stochastic gradient descent. So, to summarize our position bias estimation methods, first, we covered online randomization experiments. They are still the gold standard for bias estimation, at least under the PBM assumptions. However, as we saw, they can harm user experience. Then we covered offline intervention harvesting methods. These leverage variability in the previously collected click data, and they don't require any relevance model. However, they also assume that there is no shift in the query distribution between different rankers, and they also assume no shift of item relevance over time. So for example, if you want to use data from 3 different rankers that you sequentially deployed, for example, to your users, but you're in a domain where item relevance shifts a lot, for example, let's say news recommendation, where an article might be just relevant for a day or two, then you might not want to use this method in this way, and you might want to be sure that you use data from an A/B test. Lastly, we covered offline methods that jointly learn bias and relevance estimates at the same time. These methods are more extensible to latent variable models, so to also more complicated models, and we'll revisit some later in this tutorial. However, they require a well-specified relevance model. And if it's not well specified, we might introduce bias into our estimation part. Things like regression EM and the dual learning algorithm also might just converge to a local optimum. And as we'll cover later, we might also have a problem with potential confounding by a strong logging policy. With this, let's talk about advanced user models that go beyond the position-based model. So while the PBM that we've used so far is widely used, it considers only a very simple user behavior, especially that observing an item is independent of all other items in a ranking is a very simplifying and strong assumption. So here on the right, for example, we have a search query for the SIGIR value. The user might look at the first item and see that it doesn't contain the answer. So they might go to the second item, see it contains the answer in the snippet, they might click on the item, and then they might leave. Items 3 and 4 in this setting are never inspected by the user. So it doesn't really matter that item 4 at position 4 also contained the answer. This is what we would typically call a navigational query, and this exhibits kind of cascading behavior, where we assume items scroll a list from top to bottom and click on the first relevant item and then leave. In this setting, the examination of an item does not only depend on its position, but also on the relevance of previously seen item in the same ranking. So now we lose this independence assumption that the PBM makes. And empirically, this has been found to explain user behavior better than the PBM in certain search settings, mainly, for example, navigation queries. Why is it important that we also consider cascading position bias in reality? Well, here we see the performance in simulation of inverse propensity scoring that uses PBM assumption, the same inverse propensity scoring that we saw in the introduction under different simulated user behavior. When we simulate a user to behave according to the PBM, which is here the green line, we see the ranking performance in terms of NDCG converges to the skyline kind of best performance on this data set. However, if we simulate a user that behaves according to a cascade model, in this setting the DCM model, we see the ranker that we are training converges to a lower performance because, and this is important, the PBM cannot correct for cascading position bias. So let's formalize the cascade model a bit. Under the cascade model, a click on a current item depends on the relevance of the current item and on the examination of the current item. And the right side, this examination of the current item here, can be defined by all other items that were previously inspected in the same ranking to not be relevant. So this basically, this part here, formalizes this notion of scanning a list from top to bottom and stopping after clicking on the first item. However, there are also problems with this user model. First of all, it explains only one click. So we need extensions, for example, that account for multiple clicks in the same session. And then also it assumes that if a user never clicks, they might just continue scrolling the entire session until the very bottom, which is also kind of a strong assumption. And therefore, there are extensions for abandoning the session without clicking on anything. So under the cascade model, we encounter a problem when we want to use inverse propensity scoring. The right side here, as I mentioned before, can be kind of seen as the examination probability. But this examination probability now that we would need to correct by an IPS depends on item relevance again. And this is precisely the thing we don't know and which we want to estimate. Right? So this is the first problem. The second problem is now that examination depends on item relevance, this is super dependent on which item we're displaying. So for example, two lists of different items will have very different examination probabilities under this setting. Or just for example, swapping two items in the list will lead to very different position bias under this setting. So we have this issue of basically session level bias estimates, and the second one being, well, we can't really estimate our bias in the first place without knowing relevance. So how can we solve this? The first thing might be, okay, we pick a method that jointly estimates bias and relevance. Things like regression EM might come to mind. However, there is a nice solution by one of our co-authors from Ali, which is called session-dependent probabilities. And this is what I will explain next. Session-dependent probabilities first acknowledge this thing that under the cascade model, the propensities or the bias in our ranking differs for each ranking of items. And the second thing is it uses the observation that we can actually use clicks in the current session that we already observed on previous ranks to correct for bias. Why can we do this? So under the cascade model, users always look at the first position. If they don't click, we assume they would go to the next position. And if they, for example, click on that one, they might stop. So if we now want to predict the examination of the third position in the item, we can now say something under the cascade assumptions if we think the user even examines rank 3 or not. And we can use the clicks in the current session to estimate this examination probability. There are more details in the paper, but essentially for session-dependent probabilities, there are different formulations that all use clicks on previous ranks. So let's look at two different click models, cascading click models that were basically proposed using session-dependent probabilities. So here, note that we are basically estimating the probability of examining a current item. So this is what we would plug into our IPS estimator. The first one is the dependent click model. The dependent click model assumes that if we don't click on an item, we always continue to the next one. So this is what is, for example, captured here in this latter part. If we click on an item, there is a rank-dependent probability that the user might still continue to the next item. So this is the lambda here in the setting. And there are ways to estimate this, but they are covered in the paper. So for now, assume that we know this one. So by using the clicks that we have already observed in the current session, we can basically estimate our examination probability. The second one that we'll cover is the dynamic Bayesian network, or the DBN click model. The DBN click model is a little bit more advanced. It first assumes that, again, if a user does not click, they always continue to the next item. If they click on an item, there is now a document-dependent probability. In this setting, we call it SD, that the user might be satisfied. So if the user is satisfied after clicking on an item, they just stop the session right there and don't continue looking. But if they're not satisfied, they might go back to the ranking and look at the next item. And then there is another probability called gamma in this session, that the user might just abandon the current session at any point in time. So this is basically this abandoning probability that takes care of users not endlessly scrolling down the list. So these are two different methods. And for more details, I refer to the paper, but where you can basically plug in the clicks of the current session to get an examination probability that you again then in the end can plug into your IPS estimator to account for cascading position bias in unbiased learning to rank.
The second bias we want to cover is the trust bias. What is trust bias? Imagine a user is typing a query in a search engine, and the search engine returns a list of document to the user. As the user trusts the search engine's ability to retrieve relevant items, so they may click the first document no matter what the document is. So this may lead to the user may overestimate the relevance of the top-ranked document, and this is trust bias. Here is a user study to demonstrate the existence of the trust bias. In the plot, it shows the percentage of times an abstract is viewed or clicked by the users. So the gray bar show you the views or the examination probability, and the dark bar show you is for clicks. And we clearly observe the position bias. And for the first two ranked items, they both have very high probability to be viewed. One is over 80%, one is over 70%. However, the atom at the first position received much more clicks than the second one. There could be two reasons. First, the search engine is very good, so they put the more relevant atoms at the first position. And there could be another reason: the user trusts the search engine, so they give more likely to click the first ranked atom. So the authors swapped the first two atoms and do the similar experiments. They observed the first two atoms. Now they still got very high probability to be viewed. However, the atom B, currently at the first position, but originally at the second position, received a much higher percentage of clicks than the atom A, currently at the second position, but originally at the first position. So this, to some extent, shows us the existence of the trust bias. How to model trust bias in a click model? Trust bias model clicks on examined but irrelevant atoms. This makes it different from position bias. So in the click model, they introduce a term for the probability of irrelevant document being clicked due to trust bias. Trust bias is actually a false positive click-through rate that tends to be higher for top rankers. ranks. So that means if an atom is irrelevant, its relevance score is 0, but it's being put on the top rank position, so they still have very high chance to be clicked. How to estimate the trust bias? Our colleague Ali proposed a method to apply an affine transformation to atom relevance to estimate trust bias. So in the click probability depends on the position bias theta k, multiply the sum of the click probability given document D is relevant epsilon k plus, multiply the probability when the document is relevant, and the click probability given document is irrelevant epsilon k minus, multiply the probability the document is irrelevant. These three parameters can be reduced to 2. Here they use alpha k and beta k. Then this results in a affine click model where the click probability depends on the alpha k multiply the probability the document to be relevant plus beta k. And these two parameters, alpha k and beta k, can be estimated, for example, using the regression EM algorithm. The third bias we want to cover is the atom selection bias. So the user is typing the query in the search engine due to on his mobile phone, for example, due to the limitation of the screen, so only a few documents or atoms is displayed. In the right side column illustration, we saw 3 atoms are displayed. So any atom after that will not be displayed, so that means they don't have any chance to be examined or clicked by the user. This is the atom selection bias, and it can be seen as the extreme form of position bias with 0 examination probabilities. However, this poses a question as the standard IPS estimator requires non-zero examination probability as propensity, otherwise the inverse propensity will be invalid. There are 2 potential solutions. Stochastic policies or the doubly robust method. We will introduce this later in this tutorial. The last bias is related to atom context. The first one is a surrounding atom bias. The most model, like the positional based model or cascading model, they assume a vertical ranking list, and the user browse the atoms from top to the bottom. However, in the real world case, it may be more complex. For example, in the Netflix, they have the grid layout, so the examination may be influenced by the position or the relevance of all surrounding atoms in the ranking. Another bias related to context, atom context, is the outlier bias. The left figure show you a user is typing the smartphone as a query, and the system return a list of atoms. The third atom, it has a more descriptive field, colored tag, and the hair price, and this make it more attractive, and this could lead to more clicks on the third atoms. So these atoms with deviating features attract more attention, lead to more clicks. We call it the outlier, and this outlier may influence the user clicking behavior, and this is outlier bias. The authors also did experiments on a real-world Dutch e-commerce platform to demonstrate the existence of outlier bias. The red plot shows you the click-through rate over the ranking positions. The black dashed line showed when there is no outlier in the ranking list. We clearly observed the position bias here, where the atoms on the hair positions got more clicks. But it could be different when the outliers appear in the ranking list. we observed the CTR peak at or nearly the outlier positions, and this clearly show us the outlier in the list affect the user clicking behavior, and this demonstrates the existence of outlier bias. And how can we model the outlier bias and the context bias? So the first paper, they propose the outlier-aware positional-based model. They think the examination at rank K also depends on the position of the outlier. They introduce a term to examine rank K when an outlier is present at rank O. The second paper introduced a context-aware position-based model, and the model clicks depending on examination relevance and the comparison with surrounding atoms. They introduce a term for probability of keeping user attention given atom context Z. To summarize, in this part, we introduce 5 types of bias. The position bias, where clicks are influenced by an atom's position. Cascading position bias, clicks are influenced by the relevance of previous atoms. And trust bias, atoms on the top position may be clicked regardless of their relevance. And atom selection bias, non-displayed atoms cannot receive clicks as they don't have chance to be examined by the user. And the surrounding atom bias, the position and the relevance of other atoms may also affect the examination. There are also a few biases we didn't cover in this part, especially related to explicit feedback. They are presentation bias, confirmative bias, popularity bias, and positivity bias. If you're interested, you can go to the reference for more details.
That brings us to the third part of this tutorial about counterfactual estimation methods. This section, we're going to talk about advanced inverse propensity scoring estimation, two-tower models, doubly-robust estimation, and safe unbiased learning to rank. I'll start with advanced inverse propensity estimation. The first estimator I'll talk about is the one that does affine correction, the affine estimator. This estimator is introduced for trust bias, which we discussed in the previous section. Just to recap the important information here, trust bias is not a linear relationship, but an affine relationship between relevance and click probabilities. And you can think of that as the ratios between the ranks differ because people trust items more top ranks. So here we have only position bias. The ratio between a click on a relevant item and on a non-relevant item are the same everywhere, both just scaled down by the same magnitude. Whereas with trust bias, the ratio of clicks on non-relevant items is much higher at the start of the ranking. This represents the idea that people trust the search engine. So they'll say, well, it may not look relevant to me, but if the search engine thinks it's relevant, then it's probably relevant. So I'm going to click on it anyway. So the ratio between these two is very much lower here, but gets higher at the end. And the most prominent way to describe this sort of bias is by introducing a beta parameter. So now the probability to click is alpha k, so an alpha bias parameter multiplied with relevance, similar to what we saw with examination probabilities, plus a beta parameter, which is kind of a base rate, the amount of clicks you get regardless of relevance. This is an affine transformation, and as a result, you cannot correct for it with a linear transformation, which is what inverse propensity scoring does in the standard estimator. So we can't use inverse propensity scoring to correct for this bias. So we need a new estimator, and this is the affine estimator. We still average over clicks, but now before we weight by this weight, right, before we rate it, we subtract a penalty. So we subtract beta, and beta could be seen as the standard click-through rate that you get at a rank. So these are the clicks that this document got for free. This is whether it was actually clicked or not, and that difference is being weighted by alpha. So similar to inverse propensity scoring, we are doing reweighing, but we're also penalizing sort of the places where we expect to see incorrect clicks. What's interesting is that this is actually a generalization of inverse propensity scoring. If beta is always 0, we are back and we have sort of an inverse propensity, standard inverse propensity scoring estimator again. There is, unfortunately, right now, not a known method to find out about the beta parameter, the trust bias parameter, with a randomization method. But you can use expectation maximization methods we've also talked about, like click models, to estimate these two parameters. These are the results from the paper that introduced this estimator. This time it's NDCG at 10, so the higher the better. You can see again, if we don't correct for any bias, we don't learn very much. We get stuck at this local suboptimal place. These are two IPS estimators. One of them is the original one. The other one was designed for trust bias. You can see they don't really solve the problem. So this one is a small improvement, but it doesn't really solve the problem. This is the Affine estimator, and you can see it's the only one that actually reaches optimal performance, because it's the only one that's unbiased here and that can actually correct for the trust bias in the data. Then the next estimator I'm going to talk about is the policy aware estimator. And this estimator was designed for item selection bias. And item selection bias, you can think of this as an extreme form of position bias, and thereby also an extreme form of selection bias, where not every item can be shown on screen at once. So in this example I'm showing on screen, we have 5 items, but only 4 are displayed to users. So the bottom item here is 0% of users see it. So there's no clicks here that we can reweigh. You might see a problem already with inverse propensity scoring, that we would have to reweigh by 1 divided by 0. 1 divided by 0 is undefined, right? That's actually not really the problem. The real problem is that there's no clicks to begin with. We don't have anything to reweigh, so there's nothing to learn here. All items will have the same amount of clicks, 0, right? So inverse propensity scoring cannot correct for this if we apply it the way I previously introduced it. But this is only a problem under a deterministic policy. If we have a stochastic policy, there's more we can do. And what I mean by a deterministic policy is a policy that gives the same ranking every time you give it the same query, whereas for a stochastic policy, we sample a ranking out of a distribution. So there's a randomization that is inside this ranking policy, right? This is very common, by the way, stochastic ranking policies. In fairness, if you want to have fairness of exposure, which we'll talk more about at the end, the final section of this tutorial. For top K ranking, it's important because you can correct for item selection bias. And importantly, what we can do, the trick that we're going to do here is, instead of basing our propensity on the displayed ranking, we're going to base it on the policy. So instead of the examination of the ranking that we had before, we can now say, what are the possible rankings that would come out of our policy? What are the probabilities? We can have a weighted average, which gives us the expected behavior under this policy. And then we can get an expected examination probability. We're going to call this the expected exposure. And what happens now with the stochastic policy is that we can give a positive click probability to items that didn't have it before, because we're considering multiple rankings. So remember, in this here we have 2 rankings: a ranking of 80% that's shown 80% of the time, where item 5 was not displayed, cannot be clicked, has a 0 click probability, and 20% of the time it's clicked, it's shown at position 4, where it has a chance of being clicked. So the click probability is going to be 0.8 for 80%. The probability of being clicked here, right? But we know that's 0 because the item is not being shown, so we can actually forget about this part. Time plus 0.2 for 20% times the probability of being clicked in this ranking over here, which is going to be presumably non-zero, right? Presumably it's going to be, if it's relevant at least. So what we can do here is we can create our estimator by sort of separating the parts here. Let me show you how that happens. We have our click probability under the policy, where we sum over every position. How likely is the policy to show the item at that position? How likely is it to be clicked at that position? Which again is the examination at that position times the relevance. The relevance part is actually not dependent on this sum here, right? Because k is not involved, so we can move that out of it. So we can now have sort of this sum over here. And what you can see now that this is just what I defined as expected exposure. So the probability being clicked here is exposure times relevance. So we are now again in this setting as that IPS can deal with very well. And even if there's item selection bias, this propensity can still be non-zero. So we can create our estimator here. It's unbiased as long as every item has a non-zero chance of being displayed in the top k. If there's some randomization that could put every item in there with some probability, it's going to be unbiased. Here are the results from the paper that introduced this estimator. Well, you could basically see that all the estimators get stuck at a certain level of performance, just like before, because they're all biased, right? We're doing NECS 5, so the higher the better. This dashed line here is the estimator without any cutoff, so it's allowed to show all the items at once. There's no item selection bias. It can learn the optimal ranking, obviously, because that form of bias is not there. This is IPS as introduced before. But the policy-aware estimator is this red line. You can see it also reaches optimal performance, but much slower. This makes sense because it has a lot less information. So whereas this estimator was shown clicks on the entire ranking, this one only showed 5 items at once. So it's very limited in the amount of information it had, but still it can find out what the best ranking is. So it's unbiased and consistent in the setting. Therefore can deal with item selection bias. All right. Then the final inverse propensity scoring estimator that I'm going to introduce, or the final 2 actually, is one that combines the previous 2 advancements and one that combines online and counterfactual learning to rank. Let me first say a bit about online and counterfactual learning to rank. We've talked about unbiased learning to rank so far. What we mean by that is we're learning from clicks and we're correcting for interaction biases. The most broad term of these 3. Inside unbiased learning to rank, we have counterfactual learning to rank. I've talked about that so far. We have historical data that is already there, logged by a different policy, but we can't change anything about it, and we learn from it by inferring a model of bias. There's another family of learning to rank, unbiased learning to rank methods called online learning to rank. They correct for bias by randomizing results in online interventions. So they're interactive algorithms. They have choices to make about how data is gathered. So they can intervene. They can say they can change sort of how data is being gathered. And that's something that's being assumed in counterfactual learning to rank. You cannot do that. We assume the policy remains stable. The goal of this work was to find a framework or a method that could do both at the same time. So the question is kind of like, why are these 2 different families? Can't we find a method that does both with state-of-the-art performance? The first step is actually to combine the Affine estimator and the policy-aware estimator into a single estimator. I'm going to, it's called the intervention oblivious estimator. That name makes sense when I introduce the next estimator. But you can see here it combines the ideas of the previous ones, right? It removes the penalty for the beta parameter, but it takes the expectation, just like the policy-aware estimator did with its propensities, and then divides by the expected alpha, which is similar to the exposure that we had in the policy-aware estimator. So it does an affine transformation, but it's now conditioned on the policy instead of on individual rankings, thereby combining both. And it's unbiased if there is both position bias and trust bias as well. Okay, then the idea of the next estimator, which is called the intervention-aware estimator, was to take counterfactual learning to rank, but no longer assume that there are no interventions. What if we start with the idea that the policy can change when we were gathering the data? So I'm introducing this large set pi, right? And for every time step, it keeps track of what the logging policy is. So these are not necessarily unique policies. It could be that all of the policies in the set are the same if there are no changes. It could be that the first half is the same and the second half is changed if there was a change halfway, etc. So this is just notation. Don't think that we're changing the policy every time step. It's just notation here. We can condition the click probability now on the set of policies instead of the individual policies. And because of my notation, it's basically just an average, right? Because every policy pi here is a single time step. And now we have a click probability based on a set of policies instead of the individual logging policy. And you can take the intervention oblivious estimator and now instead of conditioning on a single policy, I can condition on the set, right? So now I'm just taking expectations again, but now on an even bigger set. This is interesting because instead of treating each click based on the policy under which it was gathered, I'm now also considering what the other policies are. We're considering all the policies used for logging data. And we can visualize it like this, right? So here on the left, we have the exposure, expected exposure. The blue line is expected exposure under the policy at each time step. So you see there's a change here at step 100. There's a 1 in 4 chance of being examined in the first 100 time steps. And after that, it's a 1 in 20 chance. So that's quite a big change. So what's going to happen in the intervention oblivious estimator, or sort of the standard estimators, they're going to treat the first clicks, they're going to weigh them times 4, and then they're going to weigh the clicks after time step 100 times 20. So quite a big difference. But they're still they're treating these clicks differently depending on when they occur. If we take the intervention aware estimator, we're actually going to look at the set so far. So the way to read this graph is to, up to this point, what would be the policy? There's only one value for the entire data set, right? So this is how that value changes. Initially, it's going to be 1 in 4, right? Because we only have that estimator. And then it turns into a weighted average between the two. So over here, it's right in the middle because half of the interactions are with the 1 in 4, the other one with the 1 in 20. So we end up right in the middle. If we continue, we're going to asymptotically move towards the 1 in 20. The cool thing is, if you now look at the inverse propensity score, it goes up much slower. So we're dealing with larger propensities, and there's for smaller inverse propensities. If you remember, this helps us with variance quite a lot. And again, we're treating all clicks the same way. We don't treat them differently based on when they were logged. Here are the results from that paper. So this is a setting where there are no interventions, just as all the previous ones you've seen, with trust bias and item selection bias and position bias. We see here the red line, the intervention aware estimator, and the intervention oblivious estimator, because they're equivalent in this setting, perform better than the other two. Not very surprising. It's the only one that's unbiased in this setting. But if we now start to introduce interventions, we see interesting differences. So interventions help all the methods, but especially the intervention oblivious method is very high variance. So what we did here is every 50 step, there's 50 interventions. So spread on this logarithmic scale, we have 50 times that the policy was updated with what was expected to be the best policy at that moment. And what you can see is that only the intervention aware estimator benefits from this the most. It finds the optimal policy much quicker than when there were no interventions. It has very small variance, so it can really effectively learn from this intervention data. Thereby, it's essentially doing a form of online learning to rank, in this case with limited interventions. We show that the more interventions you do, the faster you can learn, but there is sort of diminishing returns. So we don't actually know how far you can go before you no longer have, for this no longer really helps. All right, to give you a summary of the advanced inverse propensity scoring. I've talked about affine corrections. Only affine corrections can correct for trust bias. Standard inverse propensity scoring cannot, because it's not a linear relation. I've talked about the policy-aware estimator. This deals with situations where there's item selection bias. Not all items can be shown at once. Deterministic logging policies cannot deal with this setting. If you have a stochastic policy and a policy-aware estimator, you can. Intervention-aware estimator was the last one I talked about. This was unification of online and counterfactual learning to rank, but also of the affine and the policy-aware estimator, combining them sort of into one maybe ultimate IPS estimator. By starting with the assumption that interventions may take place, in using that in its corrections, it actually benefits from interventions quite a lot and can learn much faster. If you have interventions and you don't take that into account, like the intervention abilities estimator, the performance boost isn't as clear. You can get very high variance results. So it's really about assuming that it's there and then taking it into consideration. That's advanced IPS. We're now moving on to the non-inverse propensity scoring methods in the area.
So in this next section, let's discuss two-tower models. As you might remember from the section on bias estimation, there we looked into clique models. And two-tower models are essentially modern instantiation of the classic PBM clique model, where we use neural networks instead of just estimating our bias and relevance features by just counting, for example, impressions and clicks. In two-tower models, we have two neural networks. The first one taking relevance features, so things that quantify how relevant our current document might be for the current query, things like textual match, TF-IDF, BM25 kind of features, and we try to predict the relevance of a query document pair. On the other side, we have another tower called typically the bias tower, where we use features that we might think influence examination of an item. So mostly we think about things like position, but in this setting, we are not restricted to only using position. We might include things like the device type, because you might imagine you have, for example, on desktop, a different examination behavior than on your smartphone. We might include different item display types, how large they were displayed on screens, these kind of things. So we can include all of these features into our bias tower, and we predict a probability of examining an item. Then the two towers are combined in different ways, typically, for example, multiplying two probabilities, or there are additive versions for logits, or you have the dot product between two embeddings, and in the end, you try to predict click. During training here, both towers are combined, and we predict click, and we train on clicks to estimate the parameters of our network. But during inference, we basically only use the relevance tower of the two and rank only by the output of this network. So at inference time, this entire left part here is basically ignored. These two tower models are quite popular in industry settings, but they've been also shown recently to be decently effective. At the ULTR Wisdom Cup at 2023, a two tower model actually won the entire competition. Let's cover in this section a few things that you might need to take care of when you're using two tower models. Recently, there have been multiple papers that have been shown that if the training data that you're using was collected by a search engine that was maybe already quite good in ranking its items, training a two tower model might be a bit problematic. They frame this as position as a confounder, and you might think of this because in this setting, the position of an item and its relevance are not really independent of each other. So for example, your old search engine ranked already items by what it's believed would be, relevant items to the top, non-relevant items at the bottom. So what can happen here, for example, is that the two tower model can collapse. You might think of this if you are already training on an ideal logging policy, right? So basically in your training data, everything is already sorted based on relevance. Then in two tower models, the tower model might just learn to predict clicks based on position, right? So instead of learning are these specific document features encode a certain notion of relevance, you might just learn an item was displayed at position 1, so we predict a click, and then this tower is basically ignored during inference, so our ranking will be quite bad. There are multiple ways to address this, randomizing, for example, our training data, or as we will see, two other methods that that have been proposed using dropout or adversarial learning. So these are two different methods. We won't go into detail here, but for example, on the left side has been proposed by Google, which uses dropout, and they frame basically this position as a confounding issue using a shortcut learning setting. So as I mentioned before, in this setting, for example, you can think of, instead of learning a mapping between item features and relevance, the two-tower model might just learn a shortcut between position and relevance, basically. And by occasionally dropping out this entire bias tower, you can force the network to actually learn this relationship between features and relevance. They also propose to use an adversarial learning objective where you basically force the bias tower to not encode any signal that might be useful to also predict relevance. But for more details, I refer you to the papers here. Another thing that two-tower models are interesting for are modeling quite complex item relationships. So in the bias section, we talked about surrounding item bias. And there is actually one two-tower model that addresses surrounding item bias by estimating interactions between all displayed items using cross-positional attention. Cross-positional attention basically builds like a quadratic matrix of interactions between, in this case, all item embeddings. So basically, in this setting, we call them X, like our query document embeddings, and by position embeddings. So here they're called P. This two-tower model looks quite complicated, but in the end, what it's only doing is it's basically taking a weighted combination of your surrounding item position embeddings, your current position embedding, here PJ, a weighted combination of all of your surrounding item embeddings and your current item embeddings, feeds it through our two different towers, and then uses different combinations to predict examination. So here in this model, examination is dependent on the current position of an item, the position of all surrounding items, and the features, the relevance features of all surrounding items. And then the relevance of our current item only depends on its own features in the setting. So by jointly training this method, we can address, for example, surrounding item bias, and this has been, for example, applied to grid layouts, for example, in a Google Play setting. A second thing where two-tower models are quite interesting for is when to model mixtures of user behaviors. So you might imagine between different sessions, user might follow different search behaviors. So in some sessions, there might be more browsing, where, for example, a PBM behavior might be appropriate, or in other sessions, they might be just navigating to a single link, where they might just follow a cascading behavior. With two-tower models, there have been extensions proposed where you're basically learning a mixture distribution over different models. So there is basically a latent probability that we are learning for how likely is this current session to have been emerging from this user model or from another user model. So essentially, for a current session, we first assign it to a model and then use that for bias correction. The good thing about this is that we can model way more complicated user behaviors, mixtures of user behaviors, and we lose some assumptions that we typically have in the PBM. Again, this is just more like a rough intuition for the actual method. I refer you to the paper below. Let's summarize two-tower models. Two-tower models are neural network implementations that follow the classic PBM click model. We have a relevance tower that uses query document features, and we have a bias tower that typically only uses contextual features that encode the probability of examining an item. But typically we use more features than just position, things like device type or item type, item height. There are multiple extensions that we covered, for example, addressing the problem of position as a confounder, surrounding item bias, or how to use two-tower models to model a mixture of user behaviors. And the last thing we can mention is we'll cover the Doubly-Robust method coming up, and two-tower models are, for example, one way to also add a direct method in a Doubly-Robust setup.
Thank you, Philipp. It's my pleasure to continue by talking about Doubly-Robust estimation. And to give you some context, Doubly-Robust estimation is very well known in counterfactual estimation outside of learning to rank, but not very known inside the field. So far we haven't seen it. The first it was for a long time was sort of a hole that we had where we knew that everyone else was doing it, but we weren't doing it. To give you an idea, we talked about inverse propensity scoring a lot already. It's theoretically unbiased, but it has very high variance. We've talked a bit about regression-based estimation, for instance, with click models or two-tower models. It has low variance, but it's almost always biased. And then Doubly-Robust estimation tries to get the best of both worlds, being unbiased, but also not having this high variance problem. I'm going to start with a visualization. So I talked a lot about inverse propensity scoring, but if we visualize it, it looks something like this, right? We have a new policy on the right. On the left, we have data that's generated by our logging policy. So here I have an interaction where logging policy decided to show B and the user clicked on B. And in inverse propensity scoring, I would first compute the inverse propensities. So 1 divided by the examination probabilities or something along this line. And I would sort of make my estimate by combining the click, reweighting it with the inverse propensity, and then linking it to the probability under the exposure under the new policy. And if you remember, this is unbiased, but it can lead to high variance. That's why we often do clipping in this setting. To combine everything that we've learned so far, I'm going to introduce a notation where rho is my clipped propensity, and the expected alpha under the logging policy or set of logging policies if you want. But the maximum between that and tau to prevent too small values. And omega is going to be my propensity weight. So that's my metric weight. So that's in this case DCG weight based on the policy that I'm estimating. So omega is what we get from the metric, and rho is what we get from our logging policy. Then our IPS estimator looks like this, right? We subtract beta, and then we do the IPS estimation. This is the same thing you've seen before. My assumed click model here, by the way, is the affine click model, where it's alpha times relevance plus beta. This is unbiased. We need the propensities and we need beta to be correct. And we can expect high variance, especially when the propensities are very small. Okay. We've talked about that a lot, so I'm going to move on to the direct method. The idea of the direct method is that we use our regression estimates. So I'm assuming we have an estimator that takes the features of a document and predicts a click probability or a relevance probability instead of our observed data. So you can think of this as a magic wand. I have a model that's going to give me predictions, and I'm just going to trust what that model says. So this could be one of my two towers. I'm just going to use it as is. So with respect to the direct method, it's basically magic. We just assume it's correct, right? We don't ask any further questions. So I can predict relevance probability for every item, right? I can predict it for anything I have features for. So there we go. I've solved the selection problem because I now have a prediction for every item. I'm not missing any, and there's no selection here. And then I can just link all of these to the new policy, and I'm done, right? I have my estimate. So it's great. I've solved the selection problem, but you can imagine that there might be a problem because I'm completely relying on my regression. I'm not using any of the observed clicks. So if my regression is wrong, my estimate's going to be wrong, which is almost certainly the case. You should not assume that you have a perfect regressor in these kind of settings. This is the formal way to write it, right? So I'm just for every document, I'm just going to take the metric weight and then my regression prediction for how relevant the item was. It's unbiased if all of these estimates are correct, which is very unrealistic. So it's almost certainly biased, but we've solved the variance problem. So we're at the other end of where IPS was. We definitely have bias, but we almost certainly have almost no variance. The variance should only come from sort of what queries we observed maybe, but not from what clicks we saw, because we're completely ignoring the clicks. So we've gone to the other end of the trade-off here, right? So Doubly-Robust estimation tries to combine these two. So instead of trading them off, trying to see if we can get the best of both worlds. And really what the trick underlying it is that it realized that you can use inverse propensity scoring to estimate the error of the regression model. Let me visualize that. So again, I'm using inverse propensities here. So I'm using IPS, right? But now, instead of just multiplying it with my interaction, I'm going to look at what's the difference between what I observed, did I observe a click or not, and what I predicted. Did I predict a high click probability or a low click probability? How wrong was my regression estimate? And I can link this then to my new policy. And this is going to be an unbiased estimate of the error of my regression-based, or my direct method, my regression-based estimation. And therefore, it's unbiased, actually, because I'm now I can subtract that error. This is what that looks like. It looks quite complicated, but there's actually very nice decomposition here. All the way on the left, we have the regression predictions. So just using the regression model to predict what the DCG value of our model is. Then we get into our inverse propensity score. We still have the inverse propensity weights over here, but now instead of multiplying them with the clicks or the clicks minus beta, I'm multiplying it with the observed click minus the predicted click probability according to our regression model. So I'm doing alpha times the relevance plus beta and then minus the whole thing, right? So we get the minus there. So this is actually the predicted click probability for the position at which we've shown an item. So I show an item somewhere, I look at like, what would I predict to be the click probability based on my regression model? Did I see a click or not? What's that difference? That tells me the error of my regression, and that gives me an unbiased estimate of the error of regression. So this is actually unbiased if alpha and beta are correct. So I still need my alpha beta parameters. But for every document or item, either the propensity needs to be correct, so either this needs to be correct, or the regression needs to be correct. So if I have my propensity wrong, I can still, but my regression is right, it doesn't matter. Vice versa, if my regression is wrong, but my propensity is correct, I'm still good. So it's much easier to be unbiased here. And you can actually prove that it has lower variance and lower bias if regressions are somewhat accurate. So if the regression estimates are between 0 and twice the true relevance probability, it's going to be better in terms of variance and bias. Or at least we can prove it's better. It can also be better outside of those terms, but we know for sure in this setting that it's better. So here are the results from this paper, right? So again, we now have a metric that's similar to DCG, the higher the better. This is the production system. This is if we ignore bias. This is a setting with item selection bias, position bias, and trust bias. Inverse propensity scoring does better than ignoring bias, but can't reach optimal performance in this setting. At least not. It will with infinite data, but we've given it 1 billion queries here, and that's not enough. So it's not really feasible to expect. It still has a long way to go. I don't think you would ever see it reach that optimal convergence with any realistic amount of data. The direct method does much better in this setting. And then we see the Doubly-Robust method does even better than the direct method, although the difference there is smaller. If we look at the improvement over inverse propensity scoring, it's really large, right? We need about 1,000 times fewer data to get the same level of performance as IPS, which is a really big difference. So that's it's a simulation, but even in a simulation, this is really difficult to get. If we go to a different data set, this is the Estella data set, we see that IPS and direct method have about the same performance, but Doubly-Robust estimator is doing even better. So this shows us that it's not just sort of taking a maximum of the two, it's actually combining it in a way that's more robust, that's more meaningful. In all of the results, Doubly-Robust estimator is always significantly better, although that difference can be smaller depending on the situation with the other methods. Here it's very large. Again, if we look at sort of the performance reached over here, you need about 100 to 1,000 times fewer data to get that same level of performance, which is very impressive in even in a simulation setting like this. A downside is that initially you can have a degrading of performance. Basically, the regression which is also learned from these queries in this simulation, is so bad that it makes things worse. But if you have sufficient amount of data, this gets better. The next part of this, the next subsection is actually going to talk about a way to deal with situations like this. This is a setting where we show the full ranking, so there's no item selection bias. Now, the direct method can't converge on optimal performance, but inverse propensity scoring does converge on optimal performance. And but the direct method initially is better, and the Doubly-Robust method is, again, always better than both of them. Until the end, I mean, they both converge at the optimal performance, obviously, both IPS and the Doubly-Robust method. This is really one of the latest advancements in the area of counterfactual estimation for learning to rank. But what we have now is a nice family of inverse propensity scoring, theoretically unbiased but high variance. The direct method with regression-based estimation, low variance but almost always biased. And then doubly-robust estimation, which is theoretically unbiased with lower variance than IPS, if your regression is somewhat adequate, which should be easy to do in most settings.
All right, so let's talk about the problem of safety in optimization. Now I'll start with introducing what is the problem of safety in unbiased learning to rank. So the motivation is, so generally these unbiased learning to rank models are deployed in production in a search or recommendation setup. There's already a production system running. So the assumption is the current production system, which is running, it's safe with respect to different metrics of business metrics, user satisfaction metrics, and so on. And we collect interaction data from the safe production system, and we only deploy the new policy if it's better than the production system. So let me illustrate this point. So assume there's a semantic scholar kind of service where you search for papers. And let's say there's a query, user types in a query, and user is interested in an IR paper, and the relevant paper is on the second rank. And there are not irrelevant papers on first and third rank. So there's scope for improvement, because ideally we want the relevant result to be on the first rank. So now we deploy the system, we collect log data, we record it. Now let's say we train a new system. So this is the new system, but it ranks the relevant document to the third position. That means it's even worse than the production system. Now let's say we have another system where the system places the relevant document at the first rank. Now this is better than the production system. So now ideally we want to deploy the second system because it's better than the production system. And we don't want to deploy the first system which places the relevant document at the third position because it's even worse than the production system. So that's the idea of safety. We only want to deploy if it's better than the production system. We don't want to get worse than the production system. All right, so that was an illustration. Now talking a bit formally. So what is safe counterfactual learning to rank? Now let's say we have log data D, where you log or the system logs the queries, the displayed rankings, and the clicks. So we record, let's say, n such interactions from a policy pi naught. And the goal of unbiased learning to rank is to define a utility U, which depends on the previous production system pi naught and dataset D, and we want to find a policy which maximizes it. So this is the general goal of unbiased learning to rank. Now, what is an unsafe policy? Now, unsafe policy is when the utility of the new policy is even worse than the utility of the logging policy. That is an unsafe policy. And we want to avoid such situations. Now, what does safe counterfactual learning to rank does? It avoids the probability of such actions. So that is the probability of unsafe policy is bounded from above by delta, where delta is a fixed number. So in other words, with safe counterfactual learning, we guarantee that the probability of unsafe events or unsafe policy is some small number delta. So that is safe counterfactual learning to rank a bit more formally. Now, how do we do this? Let's again illustrate by a cartoon diagram. So let's say we have a ranking system 1 Now this is the ranking from the system. So let's say we have 5 positions and we place these documents. So this is document A is placed at first position and so on. And finally document E is placed at the 5th position. Now we are looking at the expected exposure or the exposure each document receives under the given ranking. Now since document A is placed at the first position, it receives the highest exposure and so on. Since the document E was placed at 5th position, it receives the lowest exposure. Okay, this is the logging policy. Now let's say we again have 2 different systems. So let's talk about system 1. So in system 1, we only swap adjacent positions. So this is a policy which only swaps the adjacent positions from the logging policy. That is, at position 2nd and 3rd, it swaps the documents. So now B, instead of being placed at document 2, is placed at document 3. And similarly, documents at 4th and 5th positions are swapped. Now again, let's look at the exposure each document receives. Now this is how the exposure looks like. Now, if you compare both histograms of exposure, they look somewhat similar. So that means the exposure distribution has not changed that much with respect to the logging policy. So if we are in such situation where the expected or the exposure has not changed drastically with respect to the logging policy, we call that a safe swap. So this is a safe ranking, so to say. Now let's imagine an extreme case where we reverse the order of documents. That is, instead of being placed at position 1, is now placed at position 5. And E, instead of being placed at the last rank, is placed at the first position. Now again, let's look at the exposure distribution. Now if you look at it, it's completely opposite to the exposure distribution under the logging policy. So we call such ranking or such swap of documents an unsafe swap. So this is to illustrate what is a safe swap in rankings, and this is how we achieve safety. So ideally, so in summary, we don't want the exposure distribution to look very different from the exposure distribution under the logging policy. So exposure distribution under new policy should look close to the exposure distribution under the logging policy. If that is the case, we are achieving safety.
Shashank,
Yes.
it may be a way to think about this in terms of worst case scenario. So in the worst case scenario for system 2, E that's now in front is a terrible document, but because we moved it all the way to the front, we've really messed things up.
Yeah.
Whereas if for this ranking 2, for system 1, right, you only moved it one position forward, so not that much bad could have happened.
Right.
Is that the way to think about it?
Yes, that's a good point. So if in logging policy placed a document at last position, that means it's not very relevant document. So now if we deploy ranking 3, that will really mess up the user satisfaction and so on, because we're placing a bad document at the first position. So in a way, this also avoids that situation.
Yes.
Thanks, Harrie. Okay, so that is how we achieve safety. Now again, formally, how do you optimize it, or how do you implement it? So this is the objective function. Now it has 2 parts. First part is our usual utility function from counterfactual learning to run, which we have already seen. So our contribution is the second part. So second part is a regularization term where D is the distance. You can think of it as a distance function, and rho is the exposure distribution. Now this is the distance function between exposures under a new policy and exposure under logging policy. Now since this can be seen as sort of a distance function, it will penalize mismatch between distribution under new policy, exposure distribution under new policy, and exposure distribution under logging policy. And one important thing to note is there's a weighting factor of 1 by square root of n. Now what does this new objective function achieves? So this new objective function tries to balance between utility and safety regularization. So and the effect of regularization, it diminishes by square root of 1 by square root of n. Now, what does this imply? Now, initially, when the number of logged interactions is small, so the second term will dominate, and new policy will try to stick to safe logging policy because of the distance function. And when, as the number of interactions increase, its weight will decrease and will be close to 0, and the new policy will be allowed to deviate from the logging policy. So in a way, we'll fall back to the original counterfactual learning to rank objective. This is how we achieve safety, or we deploy safely in unbiased learning to rank. Now, quickly, I'll talk about some implementation detail. So for optimizing it, we use SGD, the regularized objective, and for computing gradient, we use the trick from Bandit literature, which is reinforced trick or log derivative trick. Now, just to show how it looks like, so the gradient of the divergence looks something like this. Now, this is the gradient of log policy. So this is from the reinforce trick, and this is the reward for each ranking y. So essentially, we sample multiple rankings y, and this is the reward for the ranking y, and this is the log probability. Now, as you can see, there's an inverse propensity term again in this, so it can have high variance, this gradient. Now, can we reduce the variance? So we use a trick called baseline correction, which in summary just subtracts a constant value from the total reward. So now the question is, how do you select that constant value? So in our implementation, we just use average reward from different sample rankings. So each sampled ranking has a reward. So we just average reward across different rankings, and then we subtract it. Now, why does it work? One intuition is it lowers the scale of the reward. So the reward had an inverse propensity term. That's why it had high variance. So if we subtract a constant value, it will lower the scale and it stabilizes learning. And if you're more interested in this, you can look up on the concept of control variates. How does this actually work? So we have the results. This is from a simulated setup on the popular Yahoo Web Scope dataset. So we simulate a learning to rank situation, a learning to rank scenario. On X, let's look at this graph. On X-axis, we have number of simulated interactions. So we vary from 100 simulated queries to 1 billion simulated queries. Now, in this curve, the important lines to look at is green line and the red line. So green line is without any regularization or without any safety. It's just unbiased learning to rank. And as you can see, it takes more than 1,000 interaction to achieve the performance of the logging policy, where the performance of logging policy is just constant curve. Whereas this red line is our proposed safety method, where we add safety regularization, and as you can see, it quickly recovers the logging policy's performance. That means its performance is at least as good as the logging policy. So this is how empirically it works. All right, so that brings us to the end of this section. So just to summarize what we have discussed so far, so we have discussed a couple of advanced counterfactual estimators, including Doubly-Robust Estimator and Affine correction, so which deal with different bias setups like trust bias, and Doubly-Robust helps with variance problem of IPS. We also looked at literature on click models, or two-tower models, which are quite popular in industry these days. And finally, we looked at the advances in unbiased learning to rank, which are inspired from the latest results in offline bandit community, which is counterfactual risk minimization or safe policy learning, which we introduced for unbiased learning to rank. And we also introduced Doubly-Robust Estimator, which is popular in bandit community for learning to rank.
All right, in the next section, we will look into surveys and some applications of unbiased learning to rank in the real world to get a bit of a feeling for how it's actually performed. The objectives are, first, we will look into some real world results then into 3 case studies concerning grid layouts, user feedback beyond clicks, and a specific case of video feeds, which is quite common layout nowadays. And afterwards, at the end of the section, we will look into some implementation details that might get important when you actually want to apply unbiased learning to rank. So let's look into some real-world results. So first, let's get a feeling for online A/B testing results, because most unbiased learning to rank is actually evaluated in simulation experiments. And in those simulation experiments, we tend to see considerable performance improvements of unbiased learning to rank. However, what can we expect when we apply this in the real world? So for that, we surveyed the top 100 Google Scholar results for the terms unbiased learning to rank and went through all of the papers that did any kind of A/B test. And here we show across different methods kind of the relative uplift in a certain metric that was disclosed. Here we can only see 9 papers, and obviously the metrics are not comparable against each other, right? So we see click-through rate improvements, we see some custom metrics, we see some app usage improvement. So we want to stress that this is not comparable in a way, but for example, we get some interesting insights. For example, the very first bar on the top is when Google, I think it was in Gmail search, introduced a plain IPS correction with the PBM. And below that was when they used trust bias corrections in the same systems. So just to calibrate expectations, at least in this bar, we see kind of a median uplift of 2% relative improvements. Many results are also below, but just that you're calibrating performance improvements as this one huge outlier paper that had almost a 20% relative improvement. I think that's rather unlikely. What do we know in offline results? There are very few offline data sets for unbiased learning to rank. However, at NeurIPS 2022, Baidu released Baidu Ultra, which is a large dump basically from the Baidu search engine that was also afterwards used in the Wisdom Cup in 2023. And in their NeurIPS paper, they reported the baseline performance of 4 unbiased learning to rank methods, which I displayed to you here. So this is a visualization by us in terms of DCG at 3 and DCG at 10. So what you can see here is, first of all, the first entry here on the left is when we apply no bias correction at all, meaning we interpret clicks as being relevance indicating or not. The next one is we use IPS with PBM assumptions, regression EM, pairwise debiasing, which is a method we did not cover in this tutorial, and then the dual learning algorithm. As you can see here in this setup, where they trained different transformer-based cross-encoders for ranking with unbiased learning to rank methods, there is not really any model that can consistently across both metrics improve ranking performance on this particular dataset. And the authors of Baidu Ultra point to a couple of challenges. The first one is that real-world user behavior might just be much more complex than the biases that we tend to simulate in our simulation experiments, and there is definitely a need for more publicly available real-world datasets. The second challenge is we need more methods that integrate feedback beyond clicks. The dataset actually contains a lot of additional feedback we could use. Views, dwell time, if a user reformulated their query, all this is ignored, and for now we mostly focused on clicks in this setup. The third part is that there is some literature on methods that show that basically methods without any bias correction can perform quite well when the ranker that collected the click data is already quite strong. The fourth point is that unbiased learning to rank for transformer-based rankers, as they were used in this work, is rather unexplored, and the interactions of training, for example, a BERT-based cross-encoder on text for ranking with unbiased learning to rank loss functions is not really that known. As an upshot, in their baseline experiments, the authors found that unbiased learning to rank performed much better for frequent queries that they found in their Baidu logs. And we had seen a 2-tower model at the Wisdom Cup 2023 that basically won the competition, which used bias signals beyond just position. So that really improved the performance overall in this setup. Now, for the next part of the survey application section, let's discuss 3 case studies that might be interesting for industry applications. The first one concerns grid layouts. So far in this tutorial, we've been mostly talking about linear list layouts. However, in practice, and especially in many industry applications, we see much more complicated layouts like grids, for example. Think of image search, streaming services, or e-commerce. There are several challenges of grid layouts. First of all, we don't really know if examination may follow a left to right pattern. People might interact with grids much differently than they would interact with a linear list. Users may skip rows. Grid layouts might be very differently displayed across different devices, and items might even vary in size to have a bit more of a complicated layout, like this masonry layout here on the right. So what do we know about user behavior changes on grid layouts? For that, we cover here one study that has been done on Google image search, basically. And here the authors did an eye tracking study, and they found 3 ways that users behave differently when they look at a grid. The first part was they found middle bias. So instead of looking from left to right, top to bottom, the authors found that users much more fixated the middle items in top rows, which they then coined middle bias. The second thing is that compared to a normal list that we might have in web search, the authors found that attention decayed much slower, meaning users looked at many more items in a grid layout than they would look at in a normal linear web search setting. The third part is that after the first row, basically the authors observed that users started skipping rows while examining items. So here that's the probability of skipping each different row, and you can see there is a certain probability that people just scroll through and skip entire rows in this layout. What kind of unbiased learning to rank corrections do we have for grid layouts? We have 2 case studies from industry. The first one is from Etsy, and they propose 2 different models. The first one is a cascade model that takes this slower attention decay into account. Here we have 2 parameters. First of all, alpha, which is a fixed decay of attention when we move from one item to another. For example, when we move from left to right. And for each row, there is parameter beta, which increases attention again when you move from row to row. With these kind of cascading parameterization, you can, for example, model a bias pattern that you would see here from the right, which is taken from their paper. And they, for example, did not find this middle bias in their setting, but they basically found this kind of bias distribution that they used to correct for. The second model that they're proposing accounts for this row skipping behavior. This looks a bit more complicated, but essentially everything here in brackets is the probability of the user navigating to the current row if they don't skip any items. So if users don't skip any items, they are assumed to examine every item in every row. And once they arrive at the current row, then they navigate basically from left to right to the current item. The second grid-based propensity estimation technique was proposed in a work by Airbnb, and they proposed a 2D PBM model. So here they're basically assuming that examination depends on 2 different probabilities, one for each row and one for each column of an item. And then these probabilities are independent, essentially. This model is much more flexible than the current one, and it can, for example, model things like middle bias that we've seen before, which we displayed here. This is not a figure from their paper, but we added this here for comparison. The last point about grid layouts is that it has been empirically observed that there is really a big change in examination between different devices. So as you can see here, this is Etsy on a mobile grid, for example. There are much fewer items visible compared to a desktop grid layout. So it's probably a good idea if you have multiple device types or a mobile and a desktop layout to do propensity estimation for different device types in the set. For our second case study, we go to methods that address basically feedback beyond clicks. Why is this important? Well, in many unbiased learning to rank setups, we actually observe more than just clicks. For example, here in a very common e-commerce setting, we might first see impressions in a search setting, which in this case sweaters users might have looked at, then they might click on some, and in the end, they end up purchasing certain items. So we can track all of this. We tend to have impressions, clicks, skips, ratings of items, dwell time, and there is really a need for method to integrate more of this feedback. One method that was proposed is the joint examination hypothesis, where basically they're modeling to purchase an item, the user first has to observe the item and be attracted on the item, basically clicking on the item, and then the probability of purchase is estimated on top of that. So in this setting, both clicking and purchasing an item can imply kind of attractiveness. The third case study concerns item feeds. So feeds are something that are quite common now in social media and e-commerce setting. Think of TikTok or YouTube Shorts, this kind of setting. There are quite some differences to web search. First of all, contrary to what we so far covered, when users like what they see, they continue kind of scrolling, right? So imagine this contrasting to the cascading behavior, where we would think like the user found the item that they need in web search, they click on it, they leave. In this setting, they scroll, they find an item they like, and they continue scrolling. The second point is that users might inspect many more items. There's some evidence of people scrolling through tens to 100 items per session. The third one is it's probably better to think about personal and context-depending scrolling budgets in this setting that could be modeled. Fourthly, views in this setting can be tracked quite reliably because in feeds, almost every item takes up the entire screen. So we don't really have this problem that we would have historically in web search, where we show maybe 10 links to the user and we don't really know what they examined. In item feeds, we pretty much know if they watched a video or a picture because it's almost displayed full screen. And lastly, there are also some settings in which feeds might be hierarchical. So where people navigate onto items and then arrive at a different feed, which also has to be modeled. The one work that we highlight here was from Oliver Jönen, where they approximated examination behavior in shared chat video feeds by modeling the scroll depth per user context via a Joule-Simon distribution. So here, essentially, they use the distribution to model the probability of the user in a certain context to scroll at least to a certain rank K. This is a quite flexible distribution that they managed to parameterize with a single parameter that you can learn then for different user contexts. And the interesting thing about this work is basically, as you see here in the figure, that you can approximate many different examination curves. And these could be then personalized for different users. And you can use this not only for example, inverse propensity scoring for unbiased learning to rank, but also as part of your evaluation metrics, because this might be replacing, for example, the discount in NDCG in your setting.
Thanks, Philipp. All right, so now we'll talk about some practical considerations for learning to rank and unbiased learning to rank in general. So we'll first talk about a relevant industry topic. So how to choose between neural rankers versus GBDT rankers. So even for unbiased learning to rank, you need a learning to rank method. So how do you choose between a neural model versus GBDT model? So I'll talk about some of the advantages and disadvantages of both. So let's start with neural networks. So what is the advantage of neural networks? So one advantage, you can use dense embeddings, which are a nice way to represent features. So if you have a tabular data, so you can use dense embeddings to represent it. We can also leverage recent or latest and greatest from the deep learning area, like different architectures, transformers, and so on. And one advantage of neural networks is it scales with data. So if you start collecting more data, its performance keeps on improving. But these are some of the advantages, but some of the disadvantages it does not work very well with small tabular data sets. So if you are in a setup where you have a tabular data and less number of interactions, maybe neural networks are not the best choice, and they are not known to capture very well the higher order interactions. Now this is where GBDT models can come in. So they perform really well on small and tabular data sets. So if you are in a setup where you have a tabular features, and if you are in a small data regime, GPDT performs really well. And there are a lot of very highly optimized libraries such as XGBoost, LightGBM, and so on. These are some advantages of GBDT, but what are some of the disadvantages? One of the biggest disadvantages is it does not scale very well with the data set. That is, if you keep adding up data, its performance can saturate. So these are some of the comparisons, and you can choose or decide on the method based on your data set or setup. All right, so this was one consideration. Now we also talked about stochastic policies, previous sections, and deterministic policies. Now, how do you choose between both? So let's talk about stochastic policies. So what are some of the advantages? With stochastic policies, since they are stochastic by nature, you can collect some randomized data, which you can use for policy evaluation, of policy learning. It also helps with the in a top case setting, as Harrie previously discussed. It also helps with the fairness aspect, which we'll talk about later. These are some of the advantages, but one major disadvantage is since it is inherently random, it can hurt user experience. So if you deploy it, there's a chance it will hurt user experience. Okay, these are some of the advantages and disadvantages of stochastic policy. Now, let's talk about deterministic policies. So these are commonly used in industry. So there's no randomization for a given query. You'll see the same rank list. So there's very little chance it will hurt user experience. But some of the disadvantages is it, again, as we'll talk about in the fairness section, it's not great for fairness. And it can also, since we are showing repeated items, it can lead to boredom and churn and so on. All right, so lastly, I'll talk about some of the variance reduction methods. So this is again a very practical problem, how to deal with high variance. So if some of the common techniques are clipping, as we have previously seen, Harrie discussed in the introduction. There's one technique of doubly-robust, which again Harrie discussed previously, which can use to reduce variance. There's one more trick which is known as self-normalization. This is very common trick in bandit literature. So you use a multiplicative control variate. So we divide by the sum of importance weight scores. So this is common in bandit literature, but there's a recent paper from Ben London from Amazon. They also discuss about this use of self-normalization for ranking. All right, so that brings us to the end of this section, survey applications. So just to summarize it, we talked about unbiased learning to rank in real world applications. Some of the challenges are we need to go beyond simulation setup. We need more real world data sets, maybe some open source industry data sets. And finally, we talked about some practical considerations. How do you choose between different ranking models, different policies, and how do you deal with variance problem?
That brings us to the fifth part of this tutorial, where we're going to talk about fair learning to rank and the link between fair learning to rank and unbiased learning to rank. I'm going to start by giving a small introduction into what ranking fairness means, or fair learning to rank means, before Jin is going to explain some unbiased learning to rank methods for fair learning to rank. All right. Let me start with the motivation. Why do we care about fairness in ranking? Well, we know from what we've seen from the bias part of this tutorial that people mostly pay attention to the top of a ranking, right? If you remember, this is what position biases was all about. Ranking systems therefore largely determine which items get the most attention. And traditional ranking systems aim to order items based on their relevance, right? So we have these two observations. Ranking systems have an enormous effect on where people look, like what items they pay attention to. This is all of the biases that we correct for stem from this fact. The other fact is that they usually try to follow relevance. So they try to rank items according to their relevance. The problem that we end up with in this scenario is that differences in the attention, so the exposure items get, very rarely match the differences in the relevance of the items. So if you are, from the perspective of the item or maybe the item provider, this can seem very unfair if we think about it in a meritocratic way. So the fact that you are, let's say, 10% less relevant than another item does not necessarily mean you get 10% less attention. I think the best way to show this is by visualization. So here on the left, I have 6 items, and these bars indicate their relevancy. And you can see that although there are differences, the differences aren't enormous in this case, especially between items A, B, and C, they're relatively small. Let's say that we have the perfect ranking in this case. So our ranking system realized the correct order of relevancies and showed that ranking in that order. We can expect the exposure, the sort of the amount of attention each item gets at each rank, to follow this traditional F-shaped curve of position bias, right? If we now sort of look back on how much exposure each item got, and we compare that with the relevancies, we can see in this example a very big difference. So item A got a lot more exposure than the items D, E, and F, even though in terms of relevancy, it's not that more relevant by that degree. So there's a mismatch here, and this can seem very unfair. You can imagine in this scenario, if you are item A or B, or the provider of item A, or the provider of item B or C, you would be very upset that A got more than twice the amount of attention that you got, even though it's only marginally more relevant than the item that you provided. Okay, so this is the problem that ranking fairness aims to resolve. And usually the way that this is put formally is through looking at the ratio differences between items or groups of items. So I'll start with individual fairness. It's where we look at a per item basis. And the most common measures look at the ratio between the two. So here we have the ratio of item I to item J should match the exposure that item I got over item J. And if these ratios are in order, we would say that's fair, right? If being twice as relevant gives you twice as much exposure, then in sort of a meritocratic view, that would be fair. Of course, there are other notions of fairness. Fairness is a normative concept, right? So it's not that fairness exists. We get to decide what is fair. So you could say other things. Minimum exposure per items is something that you might see, where you would say, well, every item should get at least this amount of exposure, etc. There's a lot of things you can do here, but usually it resolves around the ratios between relevance and the ratios between exposure. For group fairness, it's a similar idea, but instead of looking at the individual, we look at the total merit and exposure over a group, or the total relevance and exposure over a group. You can think of things like content producers or product providers. If you are an e-commerce store or a media platform, usually you have different producers or providers that are like artists or movie production houses or companies that sell products to you, right? Or if you're reselling them. You want to keep them happy and make them feel that your platform is fair to them. So you can think then about sort of the items that these groups provide as a group from which you want the exposure to match the merit or the relevancy. Gender is also a very commonly used groups. So you can think about platforms where, for instance, people are looking for jobs or advertising themselves in a different way, where the platform might want to enforce a sort of equal distribution for all of the genders that are on the platform, etc. It's the same idea here, but instead of looking at the individual relevancy or merit, we are now summing over all the members of a group. And similar for the exposure, we're now summing over the entire group. Everything else is the same as for the individual case. All right. Then there are different ways to enforce fairness. I like to categorize them in three categories of how they get this fairness to work. The first one is methods that take a static approach. They try to construct an individual ranking where that individual ranking is as fair as possible. Very often, perfect fairness isn't possible or feasible in the setting, just because the exposure curve is usually so sharp that it's very hard to get two items to get the same amount of exposure, even though if they have the same amount of relevance. So this is a limited approach, but it is nice in the sense that it keeps sort of the individual rankings as fair as possible. But that's seen as the static approach. Another approach would be the amortization approach, where we are converging to ranking fairness by updating the rankings that we show over time. So the idea is that we don't just think about as an individual ranking that's shown once. We think of showing rankings repeatedly, where if we sort of take the amortization of all those rankings, they result into a fair exposure distribution. You can do this, for instance, to integer linear programming. This is some of the earliest work that brought up ranking fairness was in this category. Then we have a stochastic approach. So we've seen stochastic ranking policies before. If you have a probabilistic ranking system, you can be fair in expectation. So you can optimize a stochastic policy that an expectation is fair. I'm just going to visualize these three. I think that will, these last two at least, I think that would make it a lot clearer. So again, we have the same relevance as shown before. And the idea is now that I'm going to show 4 rankings over 4 time periods. So I'm going to start for the first time period, we show ranking 1. So this is just a ranking according to relevance. I'm just going to start by giving the item that should get most relevance, the most relevance, etc. Now, I'm going to take a running average of the exposure distribution of everything I've shown so far. So in this case, I've shown 1 ranking. This is the exposure distribution it gave me, very similar to the visualization I showed a few slides ago. This is obviously unfair, right? We see a very sharp distribution here, especially item E gets a lot less exposure than it should, whereas item E got too much. So what we can do, for the next ranking, I can show the opposite ranking. So I've now flipped the ranking. This may not be the optimal strategy. This is just an example, right? You can use integer linear programming to find out what the best ranking to show here is. For this example, I'm just going to flip the ordering to show you the principle. And now I can recompute my exposure distribution. It's a running average, so now I have the average exposure over these two. Because of the way because I flipped the ranking and the way that I had my exposure, this actually turns into a pretty much uniform distribution. This is still not fair, but you might argue this one is fairer than the previous one, that we've made a step in the right direction. If you compare these two distributions, they're actually, I think it's more fair than what we had before, right? Because the original relevances look closer to a linear distribution than this very sharp distribution. Okay. The next ranking, again, I can look at what should be done here. In this case, I'm going to show the ranking according to relevance again, because those items, like the items that are most relevant, need the most exposure more than the others to be fair. We again take the running average here, and we again have a sharp distribution, but it's less sharp now because we have this other ranking in the middle, right? I now have 2 of the relevance rankings and 1 ranking in the opposite direction. That gives me a more flat distribution. Again, we can look at what do we think is needed here. So in this case, I have the following distribution where I have B, A, D, C, E. So I flipped B and A and D and C. And then recomputing the average here. And you can see we're still not there, but slowly over time, if I were to repeat this, I would be able to match the exposure distribution. My exposure distribution would match the relevance distribution quite well, and we would have a fair ranking. So this is amortization by sequentially showing different rankings for the same query, where I keep track of what's been shown before, what the exposure distribution is that I want. We can slowly move towards a fair distribution of exposure. Then randomization. So this is using a stochastic policy. So again, I have the same relevancies. I know the exposure per rank, but now I'm going to create a stochastic policy, right? So I'm going to start by just taking the ranking according to relevancy, and I'll give that a 1 out of 3 probability of appearing. So my policy, in 33% of the time, it's going to show this ranking. Then what I've done here is the second ranking, I moved A and B down 1 rank and C up 1 rank. And similarly, D and E are down 1 rank and F is up 1 rank. So I'm sort of shuffling the top 3 and the bottom 3. And I'm going to add 1 more ranking where I did that, but then 1 more step. So this in this case, A is down 2 positions, C is up 1, and B is up 1. So it's kind of like I'm shuffling the top 3, similar for the bottom 3 there. Okay. Now I can think about the expected exposure. So when we get a query, we're going to show one of these rankings according to these probabilities. I know the exposure per rank, so I can compute what is the exposure distribution that I expect to see. And that looks something like this, right? So we see that A, B, and C get the same amount of exposure. D, E, and F also get the same amount, but there's a difference between these groups. So obviously this isn't completely fair yet, but I hope that you can see that between items A, B, and C, it's not completely fair, but it's much fairer than if I just shown the ranking according to relevance, right? So it's an improvement. I would have to make the stochastic policy more complicated. I would probably use machine learning to do that, but we could do that if we wanted to have a fair ranking policy. It would just not look very nice in the visualization. So I hope you understand the principle, and then you can see how this would work. Okay, to summarize this introduction, right? So we know that rankings have a really large effect on how attention is spread over items. Traditional relevance ranking often produces very unfair distributions of attention, where we have this kind of winner-takes-all solution, where almost all the relevance goes to the top 1 or 2 items. Fair ranking methods try to rank so that attention is spread more fairly. You can do that by updating over time through amortization. You can do that to stochastic policies. You can also try to get your individual rankings as close to fairness as you can do, albeit less effective. Many ranking fairness metrics are based around the concept of meritocracy. There are other ways to think about fairness, but this is where most of them come from, where we say the proportion of attention should match proportion of relevance. And again, you can do this on the individual or on the group level. What you've seen in all these methods so far is that we need to have relevance estimation in order to have fair learning to rank. We cannot have we don't know how to sort of match our exposure distributions to relevance distributions if we don't know the relevance to begin with. So this is where the link between unbiased learning to rank and fair learning to rank comes into play, because if unbiased learning to rank can give us good estimates of what users prefer or what they like, what they think is relevant, this can then enable fair learning to rank. Jin is now going to talk more about that link for you up next.
Now I'm going to introduce you 2 methods that combine unbiased learning to rank and fairness. The first one is FAIRCO method. It's designed for the dynamic learning to rank scenario and for the group fairness. By averaging the merit or exposure over atoms in the group, so we can obtain the group average merit and the group average exposure. There are 2 goals for the FAIRCO methods. The first one is to get the unbiased estimation of merit. Remember, we don't have access to the true value of the relevance, so we have to estimate it from clicks, which is subject to bias. And this unbiased estimation of merit will also be used in the following fairness optimization step. The second goal is to achieve fairness. They look at a merit-based exposure allocation criteria. They define the fairness matrix with using the exposure merit ratio. And they also want to achieve fairness in multiple steps or over time, so it belongs to the amortization fairness approach. The objective in this for this goal is to minimize the disparity of this exposure merit ratio over atoms across different groups. Ideally, they want each group have the same exposure merit ratio. To get the unbiased merit estimation, they use the IPS in the learning of the ranker. With the unbiased estimation of merit, we can calculate the disparity of the exposure merit ratio between different groups. Then they introduce a control term or the error term to indicate how much unfairness each group has. If the error is bigger than 0, that means the atoms in this group is underexposed. Then later, the fair co-masters will push these atoms upward to compensate for their underexposure. This is how fair co-masters work. Clearly, the ranking generated by fair co-masters is not only depends on the relevance, but also depends on fairness. In their experiments results, they consider two types of fairness. Fairness of exposure, where the groups receive exposure proportional to their relevance, and the fairness of impact, group receive clicks proportional to their relevance. The proposed fair co-method is first compared with naive method, which does not do any bias correction. In the left plot, we can observe the naive method achieve the worst ranking performance. And with bias correction, the D, unbiased learning to rank methods, improve the ranking performance. However, because it does not control for fairness, so in the red plot, its fairness performance is not good as fair co-method, which does both the bias correction and the fairness control. Another interesting finding in this paper is you have to choose a proper fairness matrix for your fairness goal. Remember, we have two types of fairness, the exposure fairness and the impact fairness. In the plot, we only observe the improvements of the fairness performance on a metric if the method is optimized for that metric. So this fair co-method has a two-step process. First is to get a ranker, then reorder the output of the first step ranker to optimize for fairness. So this kind of method lies in the post-processing approach. Another widely used approach is in-processing approach, where an end-to-end method is designed to produce fair rankings in one step. Here is an example of the in-processing approach, the policy gradient training method. Its objective is to maximize the utility while restricting unfairness to some threshold. There are three challenges to get the unbiased estimation of utility, get the unbiased estimation of disparity. So these two challenges can be done with using IPS. And the third challenge is to get the efficient solution for this optimization problem. The authors propose to use the Black-Toulouse ranking model, which allow it to use the gradient descent trick from reinforcement learning algorithm. Their experiments results. The plot show us the trade-off between the ranking performance in terms of DCG and the unfairness. We would like the right lower corner, which give you the highest possible ranking performance and the lowest possible unfairness. Clearly, only the proposed fair unbiased learning to rank method achieve this corner. Interestingly, the post-processing method cannot completely address the fairness issue shown in the purple line. So the authors hypothesized that The first step ranker is too unfair, so the re-ranking cannot completely solve this issue. To summarize, we introduced the two measures that optimize for merit-based fairness. Both need to have the unbiased estimation of merit, and they all use IPS to achieve this. The first method lies in post-processing approach, where they learn and ranker first, then reorder its output to make the ranking list fair. The second method is the in-processing approach, which aim to learn an end-to-end fair policy to generate fair ranking directly.
My pleasure to now present to you the final part of this tutorial, the conclusion section. We've been through quite a lot. What I'll do in this final part is summarize sort of the parts that we've seen before, but then also talk about some of the limitations of unbiased learning to rank and the future directions which we expect the field to go in. So, I hope the main takeaways for you of this tutorial are, first of all, that interactions are very biased indicators of relevance, that inverse propensity scoring can correct for position bias. We've seen this in the introduction. This is sort of the basis of the field. Previous tutorials have sort of talked about what happened in the field up to this part. A big part of our tutorial was to tell you about what follows after this basis. And the first thing we talked about were the other forms of bias that we find in user interactions with ranking systems. We've talked about position bias, trust bias, cascading bias, contextual bias factors, and how to estimate them, among others. So much more than the original position bias, of course. Then we talked about different counterfactual estimation methods. So we've explained advanced inverse propensity scoring, regression-based models like the two-tower models, click models, Doubly-Robust Estimation, and beyond. We've surveyed applications, so you've seen results from real-world applications, case studies, and finally, we've talked about unbiased and fair learning to rank and the connection between them, where we emphasize that the relevance estimation is really important to create fair exposure distributions. So the link between these two areas, we think, is very important and is going to stay very important in the future. All right, that gives an overview of everything we've seen so far. All the advancements or the latest advancements in the field. There have also been some advancement in understanding the limitations of unbiased learning to rank. And I want to focus on two of them here. There are three open problems for the future of the unbiased learning to rank field. There are data problems that are not statistical bias or variance. There are limitations of click-based frequency estimation, and there are limitations to click modeling. And I'll talk about all three of these, but divided into two sections. So the first one is the problem of the bandwagon effect, which is something that looks very much like statistical bias, but it's actually not statistical bias. So the bandwagon effect comes from the idea that knowing what other people think about something changes people's opinion about that thing as well. So on the right here, we see three items and the ratings that people gave. And automatically you're gonna, anyone would assume that item 2 is much better than item 1 or 3 because it has more stars and more ratings. Similarly, item 1 looks pretty bad, but item 3 might be better because the number of ratings is lower, etc. When we present items in this way, it's not just that people think about whether an item looks like what they're looking for or whether it's relevant to what they're looking for. They see what other people have said about that item in this case, and it's going to affect how they behave. And this effect is actually very problematic, and it's what we call the bandwagon effect. So a very simple model, sort of simplest version of this in the unbiased learning to rank setting would be to say that click probabilities are averages or linear interpolations of the relevance and the current click-through rate. So in this equation here, we have the click probability at a time step. So we're ignoring position bias or any, like, just assume a setting where we show a single item and people can decide whether to click on it or not. At time step n, where that probability is going to be based on the relevance, whether they like the item or not, or it looks good or it doesn't look good, and the click-through rate at time step n. So what percentage of people have clicked before time step n. So this assumes a setting where people can see this many people saw this item before you and this many clicked on this item before you. So that simulates the bandwagon effect. It's a very simple model. We have this lambda parameter here that's going to decide how strong the effect is of either the relevance or the previous click-through rate. You might be surprised to find that this model is actually unbiased. The bandwagon effect does not add statistical bias to the model, in the sense that the click probability at any n, step n, the expected value of the click probability is the same as the relevance probability. So there's no statistical bias. You might be confused, and the reason why many people are confused by this is because they are conflating unbiasedness and consistency. Unbiasedness means that the expected value matches what we're trying to estimate, right? So the expected relevance is the relevance probability. Consistency means that as we get more data, as we get more interactions in our scenario, my relevance estimates is going to turn into the relevance probability. To be more specific, if we have an infinite amount of data, in the limit, my estimate is going to match the relevance probability. But unbiasedness does not guarantee consistency in general, right? There are situations where it's the case, but they are not the same property. If you look at the figure here on the right, we can sort of see the difference between these two properties. On the top here, we have an estimator that's unbiased and consistent. This blue line shows the expected estimate over if the number of samples going from 1 all the way to 1 million. And you can see that it's always correct, right? So the expected value is always there. This interval shows the prediction interval of the estimate. So you can see that initially it can make very large errors. For instance, on one click, if we don't see a click, the estimate will be 0. If we see a click, it will be 1. So we can still, it's highly likely we go, we can go to the extremes. And this is showing the 95% prediction interval. Importantly, what we see is as we get more data, both the prediction interval becomes smaller and the expected value is correct. So we're going to converge at the right place. Here, in the second row, we have a biased and inconsistent estimator. That means the expected value is wrong, and it's also converging at the wrong place, right? It's converging, but at the wrong place. So this one is biased and inconsistent. Where the bandwagon effect brings us is this third situation down here, where we are unbiased, but we're still inconsistent, right? So unbiased and inconsistent. We see that the expected value is always right. The prediction interval becomes smaller, but actually it never disappears. So there's a point where it doesn't become smaller anymore. So we don't converge. What this basically means is that your estimate in these scenarios up here, your estimate might be wrong, but as you get more data, it's going to move closer to the expected value. Here, that may not be the case. It may be the case that you get more data and your error does not decrease. So you're kind of stuck. So importantly, this is not a form of statistical bias. It's an inconsistency problem. Now, can we deal with this, right? So in the work that proposed this problem or pointed out this problem, they tried some methods to correct for it. On the left here, we see an affine correction, very similar to what we've seen in the affine IPS estimators. On the right, it's a maximum likelihood model, very similar to the click models that we've seen before. And at the top, we see under the bandwagon effect, if you know what the effect is, if you know that lambda parameter in the click model, what can we do? And you can see we can actually do much better than just using the sample mean. But in the bottom row, we have a setting where the lambda parameter is wrong. we don't know exactly what the effect of the bandwagon is here, and we don't do much better than the sample mean. So it seems that this remains an open problem. Specifically, it's an open problem how to estimate this effect and then to correct for it as well. We know the effect, we can do some corrections, but estimating the effect and then correcting for it, that I think remains an open problem. All right, then, so that was a form of a problem that isn't quite bias or variance, but still gives us a big, like a trouble in the way that we learn from clicks. Now I want to go to the existing approach that we have and the limitations of how far we can take this approach. So what you've seen in this tutorial so far is that usually in unbiased learning to rank or counterfactual learning to rank, we start with an assumed click model. So like I'm laying out a general approach here. We start with an assumed click model, meaning we make assumptions. You've seen these equations where the click probability is some transformation of relevance. Based on that model, we then introduce a novel estimator or click modeling method. And then that's get placed into the field. So you can think of the high-level unbiased learning to rank approach. You've seen a couple of estimators that work together, that sort of fit in a framework. The corrections for trust bias that work together with item selection bias, etc. So usually we can sort of combine these contributions and get the high-level learning to rank approach. The question I asked myself at some point was, will this process eventually solve all forms of bias? If we're laying down this puzzle, is there a moment where we reach any problem that we have? So is there for all forms of bias, will we eventually be able to capture it by continuing this approach? And what I thought of was the way to find out whether this is the case is actually by reversing this. So if I start at the end by sort of what does our high-level approach look like and how it's being expanded, and if I work my way back to what are the assumptions of that, we should be able to find limitations. In the sense of we should be able to find the models, the group of models that work with this approach, and therefore also the ones that don't. Right. So the idea is figure out what is sort of the furthest this approach will take us, what is the most generic form, and what are the assumptions implicit in that generic form, because that tells us what will never be possible. To start, a lot of the estimators are click-based frequency estimation, so the Doubly-Robust method, inverse propensity scoring, they all have this form, and I give here the most generic form of it. So let X indicate any contextual bias factor. So this could be the position in the rank, this could be effective surrounding items, whatever you want, right? Just contextual bias. So as generic as possible. Most estimators that we come up with always follow this form, right? Where the relevance is an average over these clicks transformed according to their context. So the item aware inverse propensity score, the trust bias one, the generic position bias one, they all follow this form. I'm excluding for now click models and two-tower models. They'll come on in a few slides, but sort of the family of inverse propensity scoring and Doubly-Robust methods, they all follow this form. Importantly, we only have two relevant functions of this transformation, two relevant values, when the click is 1 or 0, because clicks are binary in this way. So the description I give here fits all existing counterfactual learning to rank methods and probably many in the future, right? So you can think of many novel estimators in the future that are going to fit this form precisely. Without making further assumption about the logging policy, so without assuming a specific logging policy, implicitly we are assuming there is the previous form is assuming that there is an affine transformation between click probability and relevance in this kind of shape. So some alpha parameter based on the context, some beta parameter on the context that you define this way. You can work this out from the previous formulation. So it's different than what we did at the start, where we started with a model like this. I now started with the solution. I started with the most generic estimator and made my way to this model. So importantly, we're going in the opposite direction. And an intuitive way to think about this is that unbiasedness and consistency of counterfactual estimation of this family are only possible if there's a linear relation between click probabilities and item relevancies. So here on the right, you can see that in a graph. If my item relevance increases, the click probability should follow some line, right? It should some linear relation. So there should be some straight line that we can draw there. There are other models, for instance, the Plackett-Luce choice model, where people choose between items, where this is not the case, where actually items follow a different distribution. We can't correct for those. So not with estimators of this form, which, following the trend of existing estimators, they all follow that form, right? So it seems so if we want to correct for any type of relevance pattern in this shape, we need to have something that doesn't match this form, which we don't right now. So that's a limitation of, let's say, counterfactual learning to rank. We can do the same for click models. So for a click model or a two-tower model, I'm going to categorize this under click models. We have our estimates are the result of a optimization program, right? So process. So we are minimizing some loss, where in that loss we have our estimated relevancies, we have our latent variables, and we have our observed data. Now these latent variables can be sort of the variables in a graphical model. They can also just be the weights in a deep learning model, right? So we're very generic again here. We can fit any existing method in this section. Now, what can we infer from that starting point, moving our way back to, like, what are the implicit assumptions here? They don't tell us very much, but basically we have to assume, to be consistent, that as we get an infinite amount of data, that there is a unique minimum, and that unique minimum in that unique minimum, the true relevancies are the estimated relevancy, right? So an infinite amount of data, there should be one click model that best explains the data or minimizes the loss, to be specific, and that click model should have the correct relevancies. You can tell that this isn't a big leap from where we started from, but it does tell us that if there are multiple models that could easily explain an infinite amount of data, well, we have a problem because we might not find the correct relevancies. To be unbiased, we can say even less, right? We can just say, the expected minima, the expected values that you end up with if you optimize this loss for relevancy should be correct, equal to relevance. The true relevancies doesn't tell us a lot. I think this mainly shows the difficulty in trying to prove anything for these kind of models, because the properties here depend on both the loss that we use, the model that we optimize, and how data is gathered. So it's virtually impossible to provide any guarantees here or to provide mathematical proof of any guarantees of this shape. This is just a very difficult area to theoretically guarantee anything. And it's good to be aware of that because it's an important limitation. To summarize, right, the limitations that I've talked about have shown us that not all data problems are bias problems. We talk about bias quite a lot, but there are other problems. The bandwagon effect is a very simple example of a problem that is not bias, but definitely something that would be that's a serious problem when it shows up. Click-based frequency estimation, that's the family of methods that include inverse propensity scoring or doubly-robust estimation, cannot correct for every form of bias with clicks. They do assume a linear relationship between clicks and relevancy. Click modeling cannot provide robust proven guarantees. So using click models, using two-tower models, doesn't seem that we can robustly sort of prove that these things will give us the right answer in the end. It's hard to therefore provide the conditions under which they do perform well or they don't. Lastly, what I would like to emphasize is that unbiasedness may not always be possible. This is something we see in its limitations, there's just settings or problems where unbiasedness is not what we want or not what's feasible to have. So we should not invariably expect or require it from future work. Even though we have the field called unbiased learning to rank, there are a lot of problems here where unbiasedness is not the goal or cannot be the goal because it's not realistic and it's not something that we can do. So if you're writing papers or reviewing papers, please bear in mind that unbiasedness may not be a realistic long-term goal. And there's more things to consider when we're learning from user interactions. Lastly, let me give an idea of where we think the future of the field might go towards. So, the most obvious direction, I think, is further applicability. So there are many novel forms of bias that we don't have methods for. There are also many interactions beyond clicks that we can still learn from and that still need to be debiased. We can also go beyond just correcting for statistical bias. We think a holistic approach to bias, variance, and consistency is the way forward in the future, and not just this pure focus on unbiasedness. Then there are lots to be gained in terms of efficiency. So we've seen from regression-based models, Doubly-Robust estimation, that you can benefit a lot from advances in self-supervised deep learning, unsupervised deep learning, things like relevance estimates from LLMs. Basically, if you have pretty good estimates that you've learned somewhere, regression-based estimates, you can utilize these in your estimation. So if we get an LLM that gets very good at predicting click-through rates, but it's still, noisy and biased, you could combine that with something like Doubly-Robust estimation to get sort of a best of both worlds. So this is a very interesting direction right now because these models are coming up. There are also many further directions the field can go towards. We've talked a bit about safety, where we want sort of to ensure we're not just trying to optimize the model, we're also explicitly trying to prevent worst case outcomes. So this sort of safety and robust learning that respects real world risks makes sense a lot, and there's still a lot of work to be done here. Similarly, ranking fairness and other societal and long-term effects of ranking systems are still being considered, still provide us with open problems and things to think about. So the field definitely is going to lose some of its focus on just ranking for relevancy and thinking about the other things that rankings do and what makes a good ranking system. There's a lot more to say here, of course, but for the sake of time, we're going to leave it at these directions. We hope that you find some inspiration, perhaps in your own work or in investigating this field more in the future. I would like to thank you for your attention. It's a long tutorial recording, and I'm very grateful if you made it all the way to the end. I'm also grateful if you've skipped parts through it, of course, but thanks for giving us your attention, however much you gave us. We would like to thank a couple of organizations or people as well. In the name of Shashank, I would like to thank the SIGIR Student Travel Grant and Huawei Finland Dreams Lab for both funding his research, the time he got to spend on this, but also traveling to SIGIR to present this tutorial there. Philipp would like to thank the Mercury Machine Learning Lab at Booking.com, who funds his PhD and also his conference visits. I would like to thank the 2021 Google Research Scholar Program, because they funded a lot of the time that I spent on this tutorial, and also the fact that I got to travel to SIGIR. Everything that we say in this tutorial is our own opinion. They don't necessarily represent our employers or our sponsors, but we do thank them for their contribution. Thank you very much. You can find more information in the description for the slides, and have a nice day.